of time, let's start. So we had some changes in the program for today. So we had some changes in the program for today. So we'll start with Murilo Rangel with LHC results relevant for dark matter. Then we continue more or less the program. And anyway, I will post the new version of the program for those online of the auditorium, and you can get some copies of the updated. Today it has changed. Tomorrow, for now, no changes. And for those online, we'll update the program in the web page. But for the morning, that's the main change. The first talk was switched to the afternoon, and we have then Murilo, then Pedro Cataldi from Argentina online, and then Bernard Mayros in person. Okay, thank you. So we will let you know when you have 5 minutes.
Thank you. Okay, so first of all, I'd like to thank Martín for organizing this first real dark matter meeting to try to organize or to join efforts to understand what is one of the main challenges for the next years in physics. And the organization, I also apologize that I requested to change my talk to the morning session, but okay, I'm happy that we managed. I mean, Martín managed to do that. So I guess my job here is to present well, exactly what is in the title, LHC results relevant for dark matter. I guess, is there a camera that I should, no, if I need to stay in an area, no, I cannot just go, okay, that's good. But at the same time, I guess I'm the only probably collider talk. So I also discuss a bit, and then we can also have some discussion what is happening in the collider studies related to dark matter. Actually, I didn't. So is that, should I press this one? Is it a big one or?
So what they have to switch something there.
Okay. Or maybe I can just use the yes, I think that's right. So if what is that? So what I'm going to discuss here is the two diagrams. I think that it's probably something you already know. So the two on the left, spaceborne experiments or direct detection experiments on Earth, or maybe under Earth. And what we're trying to do is to on colliders to try to produce dark matter candidates, direct production, or at some, or actually many of the results I'm going to present is to have a mediator, a new mediator that can even decay to standard model particles. But this mediator can be related to dark matter phenomena. So that's what I'm trying to convince you about. Okay, I'm not a theorist, so I'm just saying what we are looking for at the LHC and what kind of theories that predict this. So even if there is no dark matter in the detector, or there is no production of dark matter, you can be sensitive to some kind of mediator, which is connected to dark matter phenomena or theories that contains dark matter. So this is just a sketch that, okay, this is, the electron was discovered here in the 19th century. And then you have several discoveries on the 20th century. The latest discovery was Higgs boson. And then I think we, as particle is concerned, if there is a dark matter candidate, we expect that at some point we have a candidate discovered and maybe at the colliders. So what is these models about? So that's just to give you a picture. What is, so we have a series of models that can be either more complete or less complete, as stated by this reference. But what happens is that many of these models, they predict new phenomena at colliders, right? That's the most important. So they predict new phenomena at the collider, so we can test the models in our experiments in the collider, in proton-proton, or even lead-lead. I'm going to discuss a little bit. So there are models with dark photon that I will discuss a bit. There is axion-like particles that are also, even, direct, even the dark matter candidates that can be produced. I'm not going to, I don't want to scare you with this. This is, so if you are a collider physicist, you look at this and then this is easy. This is something you do every day. But if you're not a collider physicist, you have to look at this sketch just to understand that what we are looking at collider data is not one Feynman diagram. Is this Feynman diagram that can be new phenomena, plus a lot of other phenomena that most of it is related to soft interactions that you cannot really calculate using perturbative theory. You have to somehow apply a model that fits the data, and then you extrapolate to other regimes. So this is this part here, basically. Of course, these models are based on several calculations that are based on the standard model, like the evolution of, for instance, this is the proton, this is part on the density function. So you can, if you have initial condition, you can try to you have an evolution equation that you can calculate for several regimes. But this evolution equation also has limits because so I mean there are several things that play a role here. And at the end, what we are testing are the platonic cross sections. So which is the perturbative Feynman diagrams that you can calculate using QCD, electrical non-physics. But I'm just trying to to state that there are several systematic uncertainties that sometimes it's related to that we have to try to reduce. And actually at the end of the talk, I have something very nice that probably you know, but if you don't know, you're going to know today. That's also something that we can do at colliders that can help these spaceborne experiments. So in my talk, I'm going to talk about only LHC and only LHCb, right? But we can have questions about more general questions if you want. But I am just saying that I'm a LHCb member, and I'm also working on this kind of physics in the LHCb. So that's what I wanted to talk. And then this is the kind of this is the experiment we are discussing. So first, as a reminder, if you what is a particle? What can particle detectors at LHC and at colliders usually can measure? We can measure particles with lifetimes greater than 10 to the minus 8 seconds. So if a particle is unstable, but it still have some kind of lifetime that is not that small, like the pions, the muons, and especially that they are close to the speed of light. So if you consider these particles, basically they are going to interact with the detector. They are going to travel through the detector, and then you can measure the interaction of these particles with the detector. So that's mostly a particle detector, how it works. But if there are particles that are unstable, more unstable than that, like picoseconds, like the B mesons. So they are going to decay before interacting with the detector, and the decay products are going to be detected, like this particle BS0, which is one of the main reasons we built LHCb, which decays to a pair of muons. And then the muons are going to be detected. We are going to reconstruct the muon momentum, the muon flight direction. And at some point, we reconstruct this vertex. We also reconstruct a primary vertex where many particles are coming from. And then we can reconstruct a secondary vertex. We can infer that this vertex here is actually a secondary vertex, which means that this particle has a lifetime with like picoseconds, can travel like 20 millimeters in this case. And then you can detect these other unstable particles with that particles you detect. So basically that's how it works. I mean, I may be going sometimes a bit basic, but I guess that was one of the points to do that. So LHCb is a detector, which is basically we say that's fully instrumented. It means that they can detect most of the particles I listed before, like photons, electrons, muons, pions, protons, kaons, neutrons. And then we can reconstruct them, we can detect, we can identify these particles, and then we can do physics that are related to phenomena where these particles are produced. Okay, so this is the collision point, and then you see that the detector was built in this geometry because of the cross section of the B mesons that it's peaking in the forward direction, and the main it was a detector as designed for heavy flavor physics, where you reconstruct the B meson decays, and then you study CP violation or red decays. But we are also exploring the detector for more general purpose physics, like dark matter related physics, as I'm going to show you. Yeah, so we collected data, what we call run 1, run 2, and then we just started last year, run 3. So you see here there are spaces. So this is a like integrated luminosity. That's a measure of the amount of data that we accumulated. So you can see that there is like 3 years here. Then there was a stop. Another like 3 years. Okay, there is a small amount here, but it's basically 3 years. And then another stop where we upgraded the detector, and then we just started last year what we call the run 3. Of course, there was a delay because of the pandemics, but we are now collecting data with the new machine. The machine is also upgraded. LHC accelerator is upgraded. And so the dark matter related phenomena that we are interested in this case are searches. That's of course what we call. I mean, if we have found So many of the studies I'm going to present are searches and these searches are related to dark bosons. What I'm going to discuss next, long-lived particles. We have several papers on this. I'm going to cite one. Rare decays, and at the end, I'm going to discuss a little bit something we are working on about axion-like particles. And so if you here, this is a sketch of I showed you, if you know the accelerator. It has 4 experiments. And what is the difference between these experiments? So there are, of course, several technical details about the differences, but I'm just showing here what a variable which we call pseudo rapidity. Pseudo rapidity is like related to the polar angle of the production of the particles that are produced. So what we call geometric acceptance. So if you look at CMS and Atlas, they have a similar geometric acceptance, or fiducial acceptance, sometimes we call it. So you see that, for instance, the muon system of the Centro, which is in green. Alice is a bit hybrid because it's central, a bit some forward. Alice is more related to heavy ion physics. And LHCb, it was designed to have fully instrumented in the forward physics. So you see that in the forward, what we mean forward is like higher pseudo rapidity in the or polar angle. So you see that all the instruments are here. So what means that we are complementary to Atlas and CMS. We are able to have a soft triggers, which means that we lower the trigger threshold to lower energy or lower transverse energy, and this means lower mass. If you're looking for a particle with lower mass, it's going to decay in lower momentum particles. So we have to reconstruct these lower momentum particles. So lower momentum is mean lower masses reach, and a very very good secondary or tertiary vortex reconstruction. So we can measure lower lifetimes about 1 picosecond. Okay, let's go. And then at the end we have so if you look at this, also another sketch looking at the interaction strength and energy scale, and if you look where are these unknown physics that can be related to dark matter. LHCb is about in the middle. I mean, if you look at the Atlas and CMS, they are more intensity, and then you look for higher energy, while LHCb can be lower intensity. I mean, the middle of interaction strength, and then I think this is going to be clear. And there are two. In terms of dark matter, we have these model extensions where you have a clear candidate of dark matter as a particle, and then you try to detect these particle in a directed action, or you can even add LHC. If you have Atlas and CMS can do that searches where they have a missing energy, but at LHCb we cannot do that because of our geometry. So we mostly are testing these models where we have a dark sector, where there is a mediator between the dark where the dark matter lives and the standard model lives. So this is the kind of phenomena we are looking for. So the first analysis that I'm going to show is something that it's called dark photons. So as I showed here, this is predicted by this kind of sector, this kind of models where the dark photon couples with the photon, or couples with fermions actually. And then that means that it can decay to a pair of muons, a pair of electrons. In this analysis, was done with a pair of muons. And this was done in a very smart way that you can use data to predict your background, and then you try to find something that is above data. It's above data if it's in excess. For instance, here, this is one of the nicest plots. You can look at the LHC data with the dimensions, where the dimension here, the trigger here was done in a way that LHC was a pioneer experiment to do that at LHC. But now Atlas, SMS, and Alice, they're also having similar approach, where instead of saving the whole event, because I didn't explain maybe a bit, the detector is quite big. You have millions of channels, and this event at the end, one event is a kind of several kbytes, and this is happening in 40 megahertz. This is not something you can save. The data, you cannot save all the events, so you have to select events to save it. So this was done in a way that instead of saving all the events, you just save the information you need for the analysis, so that you are able to actually save every event where you have a million, and so that you can build a spectrum, a mass, dimensional mass spectrum, from the dimensional mass threshold up to higher mass, up to here is the Z0 mass. So you have the upsilon, the J size, the whole. You have all the main mesons and the bosons the boson that decays to muons. So basically, but instead you have the prompt muons, which is the peaks, and also the Drellian, which is expected to be a background. And you also have what we call quark heavy flavor, which is this dark blue. This is the muons decaying from B mesons. And you can also have a mixture of hadron, hadrons that mimic muons, like a proton that was identified as a muon, and combine it with hadron plus a muon from heavy flavor from B meson decays. So this is done in a data-driven way, that we have variables here that we can control. For instance, this variable, we have templates, and then we can extract fits, and then at the end, what we can actually measure each contribution for one of these backgrounds. And then we can search for any excess. And then since we don't find any excess, we calculate a limit. And this was, for instance, the first search for dark photomasses above 10 GeV, as you can see here. This was updated recently, where we have with more data, and then you increase, if you add more data, you increase the region where you exclude the model. And then, for instance, of course, one of the reasons is try to exclude everything here, and then say, look, forget about this model. This model, it's not. If it was true, we already have seen at our experiment. So another way to look for dark matter related phenomena is what we call long-lived particles. Long-lived particles are particles that live long enough to decay almost in the middle of the detector. So the Feynman diagram is you can produce these particles from a Higgs-like decay. So it could be the Higgs, or it can be any other scalar boson, or it could be a dark matter associated production with this long-lived particle. So the long-lived is this chi 0 here. So then it is long-lived to decays to a muon, and then you reconstruct the mass of these particles with a muon n plus tracks that like you have in your detector, you have a muon, and then you have few tracks that can be related to a vertex in the middle of the detector. Of course, these you have background for that because you have instrumental for instrumental reasons. You could find tracks that are pointing to a vertex which is in the middle of the detector, including even material interaction or miss or reconstruction issues. So this is this background is actually studied in control regions, and then you build templates, and then you fit the data, and then you see that how the data looks like here, and what is the signal would like, and then you can extract limits for the production of this kind of signal. And then this is so this is just to give an idea that these masses between for the if you assume a new Higgs like boson, you can place limits from 30 to 200 GeV, and the long-lived particles from 10 to 90 GeV. Okay, and then in these models, basically you assume that the dark matter candidates in this diagram needs to have similar mass of the long-lived particle. Even if you don't detect this dark matter, that's the limit, exclusion limit mass that you will reach in our experiment. So now actually going back a bit to what LHCb can do better, which is reconstruct B mesons. So or actually reconstructing any related meson. We could have a decay, a meson decay, like this sigma plus, where in the decay you could have a dark matter candidate. In this case, there was an experiment. There was an experiment at Fermilab called HyperCP that observed three candidates in this mass region, and it could be some indication of a new particle. And LHCb, of course, can do this also kind of experiment of analysis. And this was done with this exactly the same sigma plus decaying to proton and mu, a pair of muons. And then look, so this is the sigma plus mass you can reconstruct, and then look at the pair of muons and check if you see any peak or any that could indicate the product, the contribution of resonance. And then you don't find any resonance contribution, and then you set a limit that actually excludes what the other experiment observed. So this is a very good case, but several that you need data. You need data because if you there is never, you can never say we have enough data, you know. Because there is always fluctuations that with more data you can solve fluctuations with statistics. So that's one of the cases. Another case that we could find is like P0 particles that could decay to a pair of muons. So this is, for instance, and that was never asserted very close to the upsilon mass. So this is, you can see here, the upsilon family, the upsilon 1s to s3s. And then since many of the experiments, they don't have a resolution, the dimuon mass resolution, they always exclude these regions when they look for dimuon peaks. What LHCb is good to do is actually doing dimeal mass, low dimeal mass. So let's search for this region where the other experiments they don't look. So there was a first search on this region of the Upsilon mass, and there is of course a very details about this, how it is done, but the thing is that you search for peaks in this region, and then you of course when you are very close to the Upsilon, you have to exclude these regions, because if you have a signal which is on the top of the Upsilon, you are not going to be able to know, because you have a resonance that that exists. It's the Upsilon, and then if you have some particle spin zero being produced exactly here, no way, unless you really have a huge amount of data. So exclude of course these regions, but in these other regions where there was no previous exclusion, we now have exclusion limits closer here to the Upsilon mass. So here actually you see CMS up to here in red, and you see LHCb even closer to Upsilon masses. Okay, I hope that's interesting. And finally, so one which is not actually a search for dark matter, but it was important to as an input measurement for search for dark matters in these space-borne experiments, Pamela and AMS. So you see that this is an old plot where you could see a ratio of antiproton to proton excess in the higher energy here. And one of the systematic uncertainties, one of the main systematic uncertainties was the antiproton production. So LHCb in run 2 installed this smoke equipment where it injects a gas in the beam pipe. So the gas, of course, there is a gas flow, but the gas is really I mean, there is a flow which is not a relativistic velocity, so it means that it's a fixed target. I'm okay, right? Yeah. Okay. And then you can have fixed targets experiment here, like a proton and a helium gas, which is proton-helium, like in the rest frame of the lab frame. And then this was using data in 2016, and basically using this data, you see here you are able to identify antiprotons. Here, that's a variable that discriminates pions, antiprotons, and kaons, and then you know how to identify these antiprotons. You measure the momentum, and then you normalize, you correct for efficiencies, and then you measure the cross-section. And then you compare cross-sections with several models, event generators and models in event generators. These models are used in the Pamela and MS experiment to model the antiproton production. So you see that the models are very different from data, so you can actually constrain your models, and then you see, look, my models cannot. I have to fit now. I have to adjust my model parameters to fit LHCb data, right? So that's now I can go back and try to make an interpretation of the Pamela and AMS experiment, and that's what happens when you go back and then use LHCb results for the predictions for AMS data. You see now that you have a very good agreement of this antiproton flux. So at the end, what you see is that LHC experiments, they also can provide this kind of measurements that can be helpful for understanding the production of particles in astrophysics. And just to finalize, I wanted to show some prospects, something that we are looking for. This is called opportunity for, I think, axion-like particles in lead-lead collisions. So what is axion-like particles can be mediators between standard model and dark matter. That's not the dark matter candidate, but it's kind of mediator of this and there is a special case, of course it is a special, but why not? If these if these axion-like particles couple only to photons, one of the places to look is in lead-lead collisions. And actually CMS and Atlas already searched for these particles, and then now LHCb we are now doing analysis for that. So LHCb can go below 5 GeV. And now, so you see here, that's the exclusion plot, that's the coupling in the y-axis and the mass in the x-axis. Atlas and CMS already excluded these regions up to lower than 5 GeV. So you see here the lead and the photon, because the lead is really a photon flux goes to the Z square, and the lead is 82 protons. So that means the cross section is increased by the amount of protons square of the lead. So that's why that's the best place to search. And we have done already some detailed studies how the LHCb, so we already predicted electron photon meso-ID efficiencies. So what we see is that the main background is we call light by light, with the actually photons diphoton produced with a photon-photon collision. So this main background is actually, if you go to 3 GeV mass, for instance, you have a lower cross-section than the signal in the LHCb case, for LHCb selection requirements. So that means that it's possible to do that. And we are now analyzing data and try to, actually, this is what we expect that we could. So here you see CMS and Atlas. So we expect to probe this region of lower masses and see if there is a particle or not. So if there is not, we exclude this region. And then that's one of the contributions that LHCb can also do related to that. So I guess that's more or less what I prepared to say. So we have this program of searches that are sensitive to dark matter. I hope that you understood that it's not direct and not dark matter candidates most of the time. It's mediators that can mediate in dark matter and standard model particles. And what needs to be, I mean, if you have a model and you think that it can be tested at LHC or LHCb, you have to understand that Atlas and CMS have different capabilities than LHCb. So LHCb can do like these secondary, tertiary vortices and go to lower masses, while Atlas it's higher masses and maybe missing energy. And also there is a link here for other, I mean, measurements. There are other measurements related to dark matter that I didn't talk, but I mean, I can discuss if you want. And maybe I finished a bit before, but I guess that's all I had to say. So thank you.
Perfect timing. So we have time for questions, either from the local audience or those remote. Yes, Bernard.
So how low in mass actually can you probe at LHCb for dark photons? Because I was a little bit surprised by the fact, yeah, you show the plot at the very beginning. So
it is, so for the dineon, we actually go to the threshold 2 times the dineon mass. We actually go there. Of course, there is a acceptance, suppression, because we have to apply cuts on the muons.
Yeah.
But there is no, so if we can go to these masses, we are less sensitive, but we can go to the dimuon threshold. Now we are doing the dielectron.
Right.
And then there will be, of course, the dielectron mass.
Yeah.
But then at the maybe we are trying to go lower than that with the dielectron final state.
Yeah, no, exactly. Because the reason I'm asking, because when I left Atlas, that was in 2017, we were discussing probing masses in prompt Latin jets, final states, going up to something like 17 MeV. I don't know where that went, but I remember that 1 GeV was already using the prompt Latin jet final states that were already at that time already standard in Atlas. So that's why I was asking. But okay, 2 times, yeah, okay.
That's yeah. No, that's interesting. Yeah, I know that Atlas and CMS they are doing a lot of smart things to really go. Even they are not designed to do such lower masses.
Exactly.
Doing,
exactly.
Many smart things to reach these lower masses.
Yeah.
So
collimated final states.
Yeah,
Yeah, exactly. Yeah.
So in our case, we did this, and then that's why I think that's one of the, of course, that's one of the reasons to do the dielectron. But that's more challenging. I don't know, dielectron, we have more background.
Of course. Yeah. Okay, thanks.
Questions here, the auditorium. Questions online, if you wish, just unmute yourself. So while there are not other questions, I have a couple of ones. On the historical aspects, it's really amazing how many searches for any kind of dark matter mediators and so on has been carried out in LHC and LHCb in particular. When did this all started? I mean, when did people accelerated, or people started looking for specific signals that could be dark matter? Do you know his history? I'm sorry.
So this is, I'm not that old. No, but so this is started. When I was a PhD student at the Zero experiment in 2005 and 2006, there was already this kind of stuff. I think even before. I think so, because you always, the SUSY, right? SUSY have the SUSY models. They have candidates for dark matter. So if you look at these SUSY searches, they always, if you find something, it can always be related to dark matter at some point. So I guess there is, it's older than I think. But for the LHC, and for the LHC too, I guess, right? Yeah. Right.
Yeah, right. I mean, specifically SUSY, there were, yes.
Since hours.
Right, yes. Dark matter, SUSY, but I mean, this super broad, like anything can be dark, light mediators. And...
Well, my opinion at least, but I think that at least as people started to see that SUSY was not working that well, then all the exotic models, they started to get more track and more attention. That's why I think in the end what happened.
Yeah, I agree. I think after first LHC data, probably where the SUSY was not really easy, or it was not there. I think, yeah, so I think that's what your question, right? When we started doing all these models, not only SUSY, I think after for the first LHC data, yeah, and then this gained more interesting, because SUSY it's becoming harder to motivate SUSY with the limits, but yeah.
Okay, I think there's a lot of room for discussion, like what is beyond standard model physics, what is specific dark matter, interfaces. I love this spot. So in the discussion sessions, we can go back to that. So in the interest of time, I think we can start the next talk by Pedro Cataldi. And then we continue on these and other subjects. As you all know, we'll have these discussion sessions after the last talk, after the flash talks of today. But next talk is from Pedro Cataldi, Fingerprints of Modified Gravity on Galaxies and Voids. So it's a remote talk.
Hi everyone, they can hear me well?
Yes, perfectly.
Okay, so we're sharing my screen.
Good.
Okay. So good morning to everyone. My name is Pedro Cataldi. I want to thank the opportunity to present my work here in the first Rio Dark Matter meeting. And I'm going to present my work published in MNRAS in collaboration with Susana Pedrosa, Nelson Padilla, Susana Landau, Christian Arnold, and Baushu Lee, about the fingerprints of modified gravities on galaxies in voids in the context of numerical simulations, cosmological simulations. So, in the late 90s, two independent groups reported a strong evidence that the current expansion of the universe was accelerating or is accelerating. The large scale matter structure and the CMB data confirm this accelerated expansion universe. And as a result, a constant was added to the Einstein equations, becoming the lambda CDM model. But the questions arose to the physical origin of this cosmological constant. Let's remember that first was introduced in Friedman equation by Einstein for a static universe. After the discovery of the accelerated expansion, it was reintroduced, but it still remains a theoretical explanation for this from the theory of the origins of the cosmology constant. The quantum field theory predicts these values for the cosmological constant, but it's well known that this is one of the worst predictions in history of science, because there is more than 120 order of magnitude between the theoretical predictions and the observed values. So the reintroduction of the cosmological constant led to a change in the Einstein and the Friedman equations, according to these changes. But because of the lack of the physical explanation of this cosmological constant, this gives birth to a whole families of alternative cosmological models. So these alternative theories can be divided according to a scalar field of minimal coupled with matter, a scalar field with a non-minimal coupled with matters, and which among them there is the chameleon theory with thin shell effects, and the modified gravity models. In particular, we will focus in the modification of Ricci tensor, the FR theories, which modify the actions according to these equations, and this theory can be rewritten in terms of a chameleon field with thin shell effect. However, there is a much wider variety of alternative cosmological models. Here is a schematic map of how these families are divided up. Here is FR and the scalar tensor theories. But we know that for a lambda cold dark matter universe, the equation of motions in ecomoving coordinates are governed by the Poisson equations, with the ability to make superposition. This is very important for cosmological numerical simulations. But in the FR gravity, we have this modification of the actions. In this work, we will focus in the HUSA Wiki 2007 model of FR that is one of the few FR models that can be tested in numerical simulations. And also the FR models leave the detectable signatures in large scale, making it an excellent model to explore the deviation from general relativity. So we know that with a suitable choice of the constant of this model proposed by Husawiki, we recover the late accelerated expansion of the universe. We said earlier that in FR models can be rewritten in terms of a scalar tensor theory, introducing a chameleon field. And we have with this a new equation of motions, and more important, an additional force, the so-called feed force, with a consequent enhancement of accelerations. That is a mechanism that these kind of models have. In summary, the introduction of FR gravity gives rise to nonlinear equations. No superposition can be used in FR gravities, and for numerical codes, we have to use a grid scheme, not particle scheme, almost exclusively. It's well known that FR gravities models can incorporate the so-called chameleon's mechanisms, which are vital for the cosmological and physical viability, where the feed force is suppressed locally in heavy denser regions. So with this mechanism, we can avoid conflict with experiments and observations. In these theories, the structural formation is governed by the following two equations that they are called the modified Poisson equations. And the chameleon's mechanism is that when FR vanishes, we recover the general relativity Poisson-like equations. And for this, we have to impose that in high curvature regions, that means over density regions, FR depends very weakly on the Ricci scalar. And here we show an illustrative diagram showing screening regions. Here in purple, it represents an overdensity. That could be a halo, for example, where we see that in these overdensities, the scalar fields goes very near to zero, and as we go outside this overdensity to the outer regions, the fields start to increase until it reaches the background values. The background values is free parameters of these models, and also assuming a Navarro-Frenkie wild density profile for these overdensities, or for example for halos, we can reach to an analytic equation of these transition regions that we call screen radius. So it remains which are the values of this background amplitude, field amplitude. And we know that there are several local experiments, or for example, extragalactic scale test, or using CMB data or wind length that have been able to establish observational constraints for the background field amplitude. So here are the different experiments and the observational constraints. In particular, we will focus in the Bikram experiment using rotational curves of gas and stellar components that in theory should have different screening mechanisms, as the gaseous component is more diffuse and the feed force can be present there, and the stellar mass or the stellar component of the rotational curve in principle should be screened. So these two components, these two baryonic components, should feel different accelerations. So the motivation behind our work. Here in this figure, we are showing two galaxies from the Shy-Bond simulations. In each panel, we show the density of the gaseous component here in this first rows and the second row. And in each column, here is the particle gas or the gas density. In the middle column is the ratio between the total acceleration and the acceleration of general relativity that we showed here in more purple or green colors. These are acceleration very close to general relativity, which means that these regions are screened. And for example, in the second row galaxy, almost in all the regions, the galaxy is not screening. Equivalent to these ratio accelerations is the ratio between the field amplitude and the background amplitude, where we can see that in the first galaxies, there are many different order of magnitudes in difference, and in the bottom galaxy, the field amplitude is very close to the background amplitude. So the motivation behind our work is that until recently there weren't few or no numerical simulation that could resolve efficiently the FR Poisson equations and hydrodynamic baryonic equations. In this work, we will be focusing in partially screened halos, which means halos that are screened in the central regions and unscreened in the outer regions, and see how the morphology of the screening regions seems to depend on the baryonic structures due to the modification of the gravity potentials. And we want to quantify this effect. And well, this work will be focusing on finding in numerical cosmological simulation possible fingerprint of modified gravity effects on galaxy in voids. It's very important that there are galaxy in voids because voids are under dense regions of the COMET web, where it's more likely that the field force is present. So within the lambda CDM cosmology, there is a whole family of numerical simulation. We have dark matter only simulations. We have hydrodynamical simulation that include baryons. We have with high resolutions or with large volumes, for example, to study clustering. But in the last decade, many FR simulations began to take place, which are more computationally expensive due to the nonlinear equations. In 2019, the first FR simulation with baryons, which means a hydrodynamical FR cosmological simulation, came out that include the gravity solver of the ESCO code, which includes FR gravity, and the hydrodynamical package of the TNG simulations. So with the combination of these two simulations, we have in 2019 the come out of the Shy-Bond simulations, that is a suite of many simulated boxes with different cosmologies, lambda CDM, F6, F5, and with the same initial conditions and different mass resolutions. F6 and F5, I forgot to say it earlier, are the background amplitude of the scalar field. F6 is 10 to the minus 6, and F5 is 10 to the minus 5. So we are interested in studying galaxies in voids and with disk, spiral galaxies. So for this, we have to select which are the galaxies that we want to study in the whole simulated box. First, we have to look for voids. So we apply a 3D spherical void finder. For this, we gather the total number of halos neighbors for each galaxy, check the local Voronoi cell volume to limit our catalog to the most under-dense regions in the simulated box, and we take the halos and the galaxies within these halos that have less neighborhoods in the most under-dense regions, and we impose that at least each galaxy has a mass of 10 to the 9 solar masses. To characterize galaxy morphology, we use the disk to total stellar mass fractions, DT, and for this, we divide each stellar particle in the simulation according to the circularity parameter, that is a ratio between their angular momentum and the maximum angular momentum for a given binding energy. We selected this component as the stellar particles with circularity parameters greater than 0.5. So this is our, we are showing 4 selected galaxies of the F6 simulation with their screening regions. So inside these circles, we have general relativity, and outside we have an enhancement of the acceleration or the presence of the feed force. The first thing that we noted is that the screening regions change their shapes from spherical shapes if we see the galaxy in face-on frame to a more elliptical shapes if we see the galaxies and edge-on. So we are interested in halos. For this, we're interested in halos and galaxies that are not completely screened. A first test that we want to check was to see if the Newtonian fields of these halos, for example, here phi in, that is the Newtonian field of each halos, or the Newtonian field of the environment, did not screen the halos themselves. So we use the relations found out by Cabré in 2012, that is to perform a quick test if a galaxy or a halo is screened or not. And we found that for all our catalog in GR, in F6 and F5, the own potential gravity field or the environment gravitational field, it's not great enough to screen the halo or the galaxies. However, the test can be measured directly by inspecting the relations between the accelerations of each galaxy. Here we have the ratio between the total acceleration and shear accelerations versus their radii. In particular, part of F6 halos, we are showing here F6 halos, have a screening and unscreening ratios. For example, here in the top panel, we see that for 85% of halo catalog, all the halo is unscreened. The acceleration is 1/3 more than general relativity, and for 15% of halo catalog, we have mixed regions with general relativity gravity and with a feed force presence. On the right side of this slide, we see example of observational rotational curve for 2 simulated halos. Here we have a partially screened halo and a totally unscreened halos, and we are showing the different rotation velocity profiles measured or calculated in with different methods, using the acceleration field, using the true mass of the particles, or using the tangential velocities. Each method shares different values of rotational velocity, which in principle should be the same if the cosmology model is general relativity and the halo is relaxed. But we can see that there are differences between the methods. So this kind of difference should imply a change in the Tully-Fisher relations. The Tully-Fisher relations is a relation between the maximal velocities, rotational velocities of galaxy and the stellar mass or the luminosity. And we see in the first panel that if you use the true mass of the particles for calculating the maximum value of rotational curve, the resulting plot shows no significant difference between the three gravity models. Let me show all the plots, because each color here represents halos of different cosmology. In blue we have general relativity, and F6 is represented with red lines, and with green lines F5 cosmology. So the Tully-Fisher relations are different if we calculate the maximum. Not significantly, but if you use the dynamical mass, that is the effective mass represented by the presence of the chameleon field and the Newtonian field, we see that there are differences are graded for smaller halos where the fifth force is present, and we recover general relativity for more we recover general relativity for more massive halos. Using the accelerations fields, the enhancements of maximal velocities is in this case direct, because we are using different accelerations between cosmologies. And in the fourth panels, using the tangential velocities of the gas particles, we know that for F6 and F5 cosmologies, different gravity regimes inside the stellar disk strengthen the difference in the tangential velocity in the same stellar mass. So when more passive observational determination of this velocity became available, signs of reflecting the effects of modified gravity could be detected. So in this plot, we are showing the ratio between the dynamical mass and the true mass versus the true mass of the F6 halos, with gray dots is each halos, and in black line the median relations. Here we show the mean relations in the half mass radius, and we showing that for more massive halos, we have that the true mass is similar to dynamical mass, because in this kind of halos the fifth force is screening, and for less massive halos we have the difference between dynamical mass and true mass, and these have consequences in the concentration of the halo. Here we have the concentration of F6 halos between the effective density profile and the true mass density profile. So finally, we are studying how these screening ratios change their shape, their morphology, depending on the shape or the morphology of the galaxy inside the halos. So for this, we parameterize the screening ratios using first only a radius, which means assuming spherical shapes that are here, this axis, or using elliptical shapes. And
just to let you know, we have 5 minutes.
Okay, thanks. And from here we have that the relation between assuming the screening ratio and between a sphere or an ellipsoid conserve the volumes are nearly constant. But if we studied the axis of these ellipsoids, these 3D ellipsoids or the 2D ellipses, when we want to quantify the screening ratios, we see that there is, as the stellar disk is more prominent or is more well defined, the screening ratios start to elongate, to be more elliptical. So we quantify this in this following table, that for increasing these dt fractions, we have more elliptical morphology shapes, and we have that the major axes of these screening ratios are well aligned to the stellar disk. Well, let me pass these slides. And finally, we have the conclusion that in the Tully-Fisher relations, we show difference between cosmology when the maximal velocities are calculated using these fourth methods. That for a constant stellar mass, we had that the modified gravity models tend to have larger velocity due to the enhancement of the accelerations. That in FR, the halos are more concentrated than in general relativity. And if we take into account the dynamical density, the concentration decrease with respect to the general relativity. And finally, that the stellar disk interact with the gravitational potential in the central regions, those modifying the morphology of the screening regions. Higher these to total stellar mass fractions in galaxies cause an elongation of the screening regions. Thank you very much.
Thank you. We have time for a couple of questions. Is there any question here in the audience? We can open for questions online. If you want to ask, just open your microphone. Okay, while people think I have a question. So in this simulation, was there any attempt to do ray tracing to compute weak lensing signals and strong lensing?
No, I don't know if in Shy-Bone simulation this kind of study has been done. I believe not, but I know that it should be an interesting result. We are planning, for example, in using Shy-Bone simulations to study how the clustering and the assembly bias change between cosmological models, but I'm not aware if using weak lensing performing this in this simulated box has been done yet.
Can you go back to the plot where you showed the ratio of the true mass to the dynamical mass?
Yes, of course.
Any other questions?
Here. Here.
Up to 10 to the 75, you have a large difference, right? That I don't know. I think that could be probed maybe with strong lensing, for example, low mass strong lenses. But yeah, we can talk about that later.
Okay.
Thank you. Other questions?
Thanks.
I have one question also. I'm trying to remember the question. Oh yes, about the ellipticity. So you have shown all the changes on the concentration and so on, and they have some some interpretation, but I don't remember the change on ellipticity. Why does the ellipticity change?
So we first noticed that because in these simulations we have the actual accelerations of each particle, the general relativity, and the total accelerations, and we noticed that for with spiral galaxies, spiral simulated galaxies, the screening ratios start to be more ellipsoids. So this has a consequence because a more well-defined stellar disk modify the gravitational potential there, and this makes that the screening morphology regions or surface start to deviate from spherical shapes. And this is interesting because we can observe and measure these effects in spiral galaxies, and we can make a bridge or make a correlation or study a correlation between the stellar disk of the galaxies and where the screen surface resides. So we can make an assumption or start to test where the general relativity regime lies and where in the outer regions start to be an enhancement of acceleration. So this is one of the reasons that we focus there, and we think that the stellar disks reshape the morphologies of the screen surface.
Thank you. Okay, last time for a question. Okay, if there are no questions, let's thank the speaker again.
Thanks.
And we will start with the talk by Bernard Mayros. I don't know if I'm spelling correctly the name, pronouncing the name. It's about neutron conversion and dark matter. It's in-person talk, as you can see, and Bernard came all the way down from Sweden to here. So it's great. Thanks for coming. Great.
You know, can you hear me? No. Better? Okay. And okay, so thanks a lot. It's sorry, I want to have a timer for myself. So it's a pleasure to be here. So when I first thought about the title for this talk, I didn't think so much about it. So I just said, you know, neutron conversions and dark matter. But perhaps an even better title for the talk is what neutron conversions tell us about dark matter. So this is the typical, this nice diagram where you can see all the different dark matter scenarios, the weak scales and neutrinos, etc. And what I want to show you today is that neutrons actually deserve their own branch in this forest here. Okay, so dark matter. Of course, I don't think that I need to explain dark matter to this audience, but I think that we can agree that all evidence that we have so far is gravitational and astrophysical. The evidence, at least to the problem, is abundant, but its nature, it's unknown. And I like this very much. I took from the website for this event, and I like very much this this statement here. Perhaps the only certainty we have until now about dark matter is that it has become an eminently interdisciplinary field involving large sectors of theoretical and experimental physics, astronomy and cosmology, and instrumentation and data analysis. And what I'm going to show today fits very well in this in this statement. So okay, so then to the talk now. So why neutrons? So and this is very much very much connects to what Murilo was explaining this morning, because neutrons are observable portals to dark sectors. So as these mediators that Murilo was talking about, they are most of the time. I will go into direct a little bit in terms of direct dark matter searches, and we use neutrons as well a little bit. But I think that the existence of a dark sector that interacts primarily gravitationally with the visible, with the standard model sector, has been postulated a long time ago to explain astronomical data. And then when this dark sterile sector is assumed to have particles having gauge interactions similar to the standard model interaction, then this implies the existence of the famously sterile neutrinos, but also sterile baryons, right? And the reason why these are observable portals to dark sector is because any mixing between a stable, like, you know, a stable particle like the photon or a metastable neutral particle like the neutron allows the conversion into a dark parton particle. So if you think about, of course, I mean, you can't have neutron oscillations, but you can't have proton oscillations because, of course, you have to conserve charge. And one of the simplest models that you have is that we look for in this neutron searches are called the mirror matter, the models. So in this theory, I mean, the theory of mirror matter, the hypothesis that the dark sector is represented by a replica of the standard model. So that's as simple as that. So this SM prime interactions in the mirror sector, they are assumed to be in this simple model to be the same as in the ordinary standard model, but they do not interact with each other except by common gravity. So, and the mirror sector, or, you know, the particles that appear in the mirror sector, they're potential dark matter candidate. Okay, so in terms of searches of what we can do, this is again what Murilo was explaining in his talk. The photons may become dark photons via this kinetic mixing. The neutrinos can oscillate to sterile neutrinos, so there is a lot of activity on this, you know, in the ice cube, for example. And the neutron is likewise also a portal to beyond standard model physics, including dark matter. As I said, so this is a quasi-stable electrically neutral particle that can be copiously produced. But if you think about the other searches, we have comparatively few high sensitivity searches with neutrons. And this is because the infrastructure requirements that you have on neutrons. So producing neutrons is hard. But this this will change soon in the future with the advent of the European Spallation Source, where I work, which is where my research is focused on. And this is a game changer because the ESS is a neutron factory. So we'll explain a little bit about that. So okay, so ESS. So this is an area view of the field that we have in our beautiful Lund. So the ESS, so it's what we call it is at what we call the intensity or the high precision frontier. So the research that Murilo was talking about, it is in the context of the high energy frontier. So this is a little bit different because we are searching for rare phenomena. And the advantage of this, of course, is that we are sensitive to scale of new physics substantially in access to respect to colliders. Of course, I mean, there's a price to pay. I mean, what Murilo can do in LHCb or what people can do in Atlas, they have this general purpose experiments, so searches, but we are searching for one specific rare phenomenon, but the advantage is that we are extremely sensitive to this. And of course, I mean, the high neutron intensity of ESS is a crucial element of this aspect. Okay, so I want to flash this statement here because about fundamental physics as CSS, because if you DSS normally it was designed as a neutron science as a material science facility. But when we think about the neutron at ESS, the neutron is the patient rather than the probe, because I mean, if you normally you want to produce your neutrons so that they scatter with the material, you produce them at some wavelength that you're interested in, and you probe your material. But here is a little bit different because we want to see what the neutron itself is doing. Okay, so the neutron, the ESS is going to be the very fantastic neutron factory that's already been built. It's going to be the high intensity, the highest intensity spallation source in the world. It's under construction. The user program starts in 2027. It's going to fire 2 GeV protons with 3 millisecond long pulses, which hit a rotating tungsten target. If you think maybe leave for discussion, maybe some students can tell me why you think this target is rotating. We can go to that a little bit later. And it produces the cold neutrons after interactions with moderators. So producing this, and I will talk a little bit about moderators in a second. So it produces this fluxes of neutrons 10 to the 12 or 10 to the 13 neutrons per second, which is unprecedented in neutron production. So, and this is a diagram, the schematic view of what the elements, the typical, the accelerated elements here, the Kleiston gallery, and here this is where the spallation happens, and then it conducts the neutrons are guided here to the instruments, using neutron guides. Okay, so this is a little animation how this works. So you can see here the protons are hitting the target, and boom, spallation, another pulse. Okay, so thinking now about searches searches for neutron conversions themselves, not only about the infrastructure. So of course, the reason I want to talk a little bit about the reason why we do spallation, of course, because neutrons, they're abound in nuclei. So, and it's not, you need several MeV for liberating them. So, either you do fission but that's uncontrolled, or you do spallation. And that's the reason why we do it. And we have also, we have timing information for that because we have a pulse, and that is very important to suppress background. But of course, if you're interested in neutron conversions, that means, neutrons converting into an anti-neutron or into the sterile neutrons. We want two things. We want to observe them for as long as we can, to give them chance to do rare stuff, to allow them to do this. So we want these moderators to produce as cold neutrons or even ultra cold, but at this point we don't do this at ESS. So but the standard moderators at ESS, they produce already neutrons at millielectron volts. So, but we also need we need lots of collisions, of course, with this moderation. And of course, another thing that we want, obviously, is to have as many neutrons as possible. And that's why we need the ESS. And this is just to put a little bit in context to jargon. This is the energy range where we are producing the neutrons at ESS, and we are actually at this very moment designing 2 other moderators. So it's in the simulation stage where we can producing ultra cold and very cold neutron moderators, but this is work in progress. Okay, so now I want to talk a bit about my experiment, high beam and bar. So this is a 2-stage experiment that will happen in 2 stages. So the first stage is called high beam, and the high intensity bearing extraction and measurement. Yeah, well, just name. And it's to happen in the late 2020s. And this is where we're going to do the world leading searches for N to N prime. So the sterile neutrons that are connected to the dark matter. So that belongs to this dark sector that also Murilo was talking about. And we're also going to do N to N bar to N, a neutron to anti-neutron, but with lower sensitivity. because compared to, and the reason is just because compared to the second stage and bar, the flight path is going to be a lot shorter. But we're also going to use this stage to do R&D for the full experiment. And in the second stage, then we will go into improve the sensitivity to oscillation probability by 3 orders of magnitude, which is absolutely fantastic. Well, compared, and I'm comparing this to previous free neutron searches that, and the last one was done in the 90s at the Institut Langevin in Grenoble. Okay, so this is a view of where an bar is going to sit, and this is where high beam will be. Okay, so this is this is an experimental talk. I'm not going to dwell into a lot of math, but this is just to show you what we mean. Why do some of the things that we do in the experiments are needed? So if you write your Schrödinger equation to try to come to this expression. So this is what we want here. I'm going to show a diagram here, but this is what it's happening here is that the neutron is going to an anti-neutron via sterile neutron. And never mind all the terms here, but what's important here is just to see that the terms here that couples the neutron to the n bar prime. So this is the anti-neutron in the prime in this dark sector. And what's different in terms of and the reason why this is important is because the magnetic field of the dark sector is important so that you can increase your probability to see an oscillation. So when you're talking about free neutrons, then this is you want to have when this is not the case. So you're not doing this via sterile neutron. You're just doing one flip. So the neutron goes directly from neutron to anti-neutron. So then you want the magnetic field to be 0, basically. I mean, you want to, I mean, of course, experimentally, you know, that's not possible, but you want to be less than 10 nanotesla. But for high beam, in the experiment that we do magnetic searches for sterile neutrons in using magnetic control fields, then we need that condition to be true. So that's why we see it. So it's basically what you are doing here is to achieve to reach a resonance condition basically between the fields, you know, the magnetic field in our world and magnetic field in this dark sector. That's basically it. And that's why when you do this, the figure of merit, when you're doing n-to-n bar, normally will be nt squared, but since you're doing 2 flips here, then you go to then it's nt to the 4th. So, and this is actually to show here how the search is now without math, with probability is going to be more interesting to people, because I mean this is how it works. I mean, what you do is that you have a beam of neutrons, and you want this, of course, to be as long as possible. You want to have as many neutrons as possible, and there are different ways that you can do this experiment. Either you try to see if the neutron flips to an n prime or to n bar prime, then it will pass through. If you can put a beam dump here, a beam stopper, and then of course, since it's in this dark sector, it will basically goes past here the beam dump, and it flips back and appear on the other side. And then if it flips back to a neutron, then you can put a neutron counter here. Basically, I mean, of course, I mean, you need to control for backgrounds, this sort of stuff. But if you're starting seeing counts above background here, then you basically know that you're seeing something. But the only way that this can actually work is, of course, if you're scanning the magnetic field. And this is the same idea here happens with disappearance. So the disappearance, you don't put the beam dump. What you're doing is a disappearance experiment. So you are you have a flux of neutrons and that you're counting very precisely, and then you're scanning the magnetic field, and through the scans of this magnetic fields, you have to be able to count a decrease in the flux of this, so basically to tell you that there was a disappearance of neutrons, and you associate this disappearance of these neutrons to these neutrons going to a dark sector. Another possibility is that instead, I mean, as in the regeneration experiment, since this can flip to a neutron, I mean, this can also flip to an antineutron. And then if that happens, then you put an annihilation detector here. And so, and the reason why this experiment here, of course, is less, I mean, is hard in the sense that, I mean, well, you might not see anything, but if you see it, you're really going to know it. I mean, there is nothing really in nature that could do that. So this is just to show why this is important that we control the magnetic field. Of course, or the way that we're going to do this, we're going to do this by having this 3D current coils so that we can scan the magnetic field. And we also, I mean, if there are non-uniformities, then we can reduce this by putting this very expensive mu metals. And what's important here is that, I mean, of course, I mean, since you want to achieve this resonance condition, what's important for you is actually that you have that the steps that you go in magnetic field that they are small. So you have this. We have to achieve this at this level of 2 milligauss. Okay. So going on. And this is a little bit how this is going to work. So regeneration experiment here already showed this in high beam, and these two plots here to show you the sensitivity that we have to oscillation times as we scan the magnetic field. And as you can see here, we compared this to previous ultra cold neutron searches. And of course, I mean, we're going to, for the most of the phase-space region, we are going to be very fast, a lot more sensitive to them. I mean, the only and the reason is because, I mean, they didn't do I'd say a very precise job of the magnetic field of scanning the magnetic field. That's why they're extremely sensitive to one particular point here, where they, that's where the magnetic field in the standard model and then in the dark sector, they matched in this and that condition that I showed before in the equation. So but that's basically the only point in phase space where we're not going to beat them very fast. And of course, I mean, and also if you see here the things that we can do in in terms of regeneration, and of course, I mean, regeneration is this two-order process that I was talking about. So it stays below here in this, it's less sensitive, but the disappearance is only one flip. That's why you cover a larger area of sensitivity a lot faster. But as you can see, of course, I mean, it also depends on what detector radius you're able to produce. I mean, if you're able to catch lots of neutrons, then your sensitivity is going to be a lot better. Okay, so neutron detectors. I will just show just very fast here how these things are done. So of course, when you're talking about this neutron experiment, so they need very different neutron detector requirements. So in the regeneration experiment, this is you need a low flux, large area, position sensitive neutron detector, so these detectors are these are standard detectors in neutron physics. But this other detector here, detector B, This has to be a high flux, high efficient neutron detector sensitive to intensity variations of 10 to the minus 7. So you're pushing the envelope quite a lot here. And this is, and this is pretty much work in progress. So for detector A, so the technology that we're considering is this called solid state neutron detectors or helium-3. Other technologies also exist or are reaching maturity, and the ESS is actually the one of the places where you have lots of experts in neutron detectors. And for detector B, the technology that we're discussing is a thick helium-3 detector, 20 to 40 centimeters along the beam. But I mean, this is, as I said, this is really work in progress. I mean, because I don't think that at this stage nobody knows if this if this detector is going to be sufficient for the intensity for the resolution that we need in terms of intensity variations. Okay, so I talked about the neutron detectors. Now I'm going to talk about annihilation detector, and the annihilation detector is of course also very cool. So it doesn't matter really how it happened, if it was how it happened, but or I mean, you actually don't know what kind of model or what kind of physics produces this. But what we can actually do in this experiment is actually, well, once an anti-neutron has been produced, that's you can this anti-neutron is we're going to put a carbon target at the end of the beamline. This is going to interact with a nucleon in the carbon 12. Well, it's natural carbon actually, but and then it's going to produce this multi-pion finite state. And in terms of what you need for producing this for this detector, what are the requirements? Of course, you have to reconstruct the multi-pion finite state. You have to be able to reconstruct the invariant mass of the event as best as possible, but also of the pi zeros, right? That will decay to photons. You have to be able to identify the particles in the final states, and you also have to be time sensitive in order to be able to reject cosmic rays or other out of time backgrounds. So these are the elements of this detector. The annihilation target, which I'm talking about, need to have a tracker for the charged particles, a time of flight system before and after the trackers, as I said, especially for the charged pions, and for the cosmic rays. A calorimeter, of course, an electromagnetic calorimeter, and technology that we are using or discussing in simulations right now. It's a lead glass electromagnetic calorimeter, and a cosmic veto system as well. I mean, an active cosmic veto system. So we, because you want to be able to, to deal with the cosmic rays as they come, but you also want to veto them as best as you can. This is the detector that we have right now that exists only in simulations. Scintillator modules for here. This is a hadronic range detector, lead glass blocks, and this is to reconstruct the pi zeros. And of course, the tracker is going to be a TPC, a time projection chamber, or I mean, it's well, at least right now, that's the technology that we are discussing. It's nothing is settled yet. This is R&D. And this is an event display of annihilation event here. You can see this is very nice. And this is actually, this is a lot. And this is the Geon simulation. You can see here the NN bar going to 5 pions, and and you can see, of course, as I said, the pi zero reconstructed from the pi zero decay. and this is the sort of the resolution that in simulations in geons that we can reach right now, and this is the what you expect in terms of momentum for your signal pions, right? So of course, I mean, this depending on what technology, what calorimeter technology you use, you might be able to do better than this. But we have also tested other more standard technologies like this called liquid argon sandwich calorimeters that Murilo knows everything about. But it didn't improve that much. Actually, I mean, this is one of the best calorimeters in simulations that we actually found. Okay, so now I want to talk about a little bit briefly about dark matter searches in rare neutron decay. So everything that I was mentioning before in terms of these searches for serial neutrons, they are connected to these dark sectors, but as Murilo is saying, they're not a dark matter particle. And of course, I think that needless to say that the evidence of a dark sector would, of course, be groundbreaking. But this evidence would shed light on the nature of dark matter and not really tell you, what dark matter is. So another possibility, of course, is to search for neutron to dark matter. So, and one of the more interesting, I think, reasons to do this is because the dark matter hypothesis has been raised as a means of explaining a lifetime discrepancy of the neutron, which I will very briefly explain what it is. And I mean, and also because these models of neutron to dark matter, they have some success, or a fair success, I heard, in accounting for at least part of the observed dark matter. So going to the actual problem, this beam versus bottle neutron lifetime. So the way this goes is the following. So in bottle experiments, you put a set of ultra cold neutrons in a container, and you count how many remain after a certain time has passed. So it's as simple as that. But you can also you can do this in another way. You can use a beam experiment and observe the stream of neutrons and count the number of protons that you create from the decay. So in this, as you know, the free neutrons, they decay on average in 15 minutes. So of course, your neutrons do not do that because they're bound neutrons. But there is a discrepancy between what you observe between the beam and the bottle experiments, and it means that the beam neutron lifetime is roughly 10 seconds longer than the bottle. At almost, people quote this value in different articles between 4 and 5, but if you do the math here, it's almost 5. So what could it be? Well, either this is an unknown systematic uncertainty that people, that's a boring explanation, I think, but it could be, right? But let's not dwell into the boring explanation. Let's do something, that like this gentleman done in this article here in 2018, they assume that the neutrons decay 1% of the time into dark matter particles. So, and the reason why this would explain, of course, is because this beam experiment would not detect decays, this dark matter decays, and the inferred lifetime would appear longer than the actual lifetime. So that's basically it. That's what's behind it. And in some scenarios, the neutron dark decays, they are accompanied by a gamma. So here, for example, you can see this is not a Feynman diagram. I wouldn't call that, but it's a diagram. A possibility. This possibility has experimentally tested for gamma ray emission from a bottle of ultra cold neutrons. This was monitored. And this collaboration of people here, they didn't find any signal in the photon energy range between 782 to 1064 keV, and so this was ruled out. But of course, scenarios that produce lower energy gammas or no gammas at all, they're still possible. And they might be tested by looking for anomalies in nuclear decays. But this was in 2018, and in 2022, people at Oak Ridge National Laboratory, they tested, they did the first search for neutrons oscillating into dark matter mirror neutrons using this disappearance and regeneration technique, the same that I explained that will be used in high beam. The neutrons that they used were made at the spallation neutron source, and for in their experiments, the neutron mirror hypothesis was strongly disfavored as an explanation to the beam bottle discrepancy. So it doesn't mean that's not true, but it was strongly disfavored as those things go. But of course, the neutron mirror hypothesis itself is far from excluded, as I showed. The high beam experiments, the first stage of that we will do at ESS, will explore a very large parameter space already in a few months of running. So the story is not it's very far from over. Okay, so future measurements. I mean, if you think about also the competitive limits that exist from a single nucleon decay, they of course come from this very large volume experiments like super Kamiokande, for example. So they put in for neutrons, they put the limits ranging from 10 to the 31 to 10 to the 33 years. So Hyper K will of course push, either discover or improve these limits. They will start data taken in 2027, and it will of course further explore rare neutron decays, including dark matter. But of course, I mean, I also want to say that, as I showed you, our annihilation detector could also potentially observe neutron decays. This is a sophisticated detector. I mean, why not? Of course, I mean, in terms of limits, and in terms of the physics that you can reach, you cannot compete with Hyper K, not even beat the super K limits. The only situation where this would not be true is, of course, I mean, if there would be models which cannot be solved at these experiments, we don't know, we are investigating, or if the limits that they have are not applicable to free neutrons. So this is something that could happen. So possibly, and this is something that we're just starting to actually think about, we could look for dark matter in high beam and bar in this case, but I mean, I have zero results on this. This is just me saying that we're thinking about this, and this is, we're going to do some, Monte Carlo phenomenology, bump hunting, this sort of thing that needs to happen. Okay, so our collaboration here, we're 26 institutions, 8 countries. It's our white paper was signed by had over 100 people signing the paper. Our conceptual design report is to be delivered this year. Yeah, we have all this funding here, not very interesting. And what is interesting is that I want to mention is that there is potential for institutions all over the world to get involved, and we only request in-kind contributions. So basically, if you're interested in the work, please join. And I recently got a grant for a collaboration with Brazil, with Stint. This is a Swedish funding agency, and this and this I'm very happy that this is happening. There will be more collaboration with Brazil. Okay, so summary. So I think that I hope that I convince you that neutrons are one of the most important portals to dark sectors. They're complementary to photons and neutrinos. So dark sectors, they actually may be the first clue to the nature of dark matter. With the advent of the ESS, this will allow searches via sterile neutrons also in the high beam NMR experiment. Other future experiments, such as Hyperkamiokande, will be sensitive to direct dark matter searches in rare neutron decays. And I mean, high beam NMR could also enter this activity. This is under investigation. I also want to say again, more collaboration between Brazil and Sweden is extremely welcome. And this STIN project is to start in May 2023. So please, students, offline or whenever you want, please get in contact. Thank you.
Great, thank you. We have time for questions. There's one question there. You had a question. Okay, students first.
I'm sorry, but could you repeat the part? Why the use of ultra cold neutrons and this relationship with the temperature and the results?
You mean?
I think in the third you showed the temperatures and you said that the use of ultra cold neutrons.
The table?
Yeah.
No, I mean the table, of course. Let's see this one. Yeah. Well, this is, I mean, this is just to tell you what to tell you what the jargon is. That's one reason why I showed it this table, because I mean people are always in neutron physics talking about ultra cold and very cold, and of course I mean the reason why ultra cold neutrons are good for doing this sort of experiment goes back to what I was saying before. You want them to go as low as possible. So if you could do an experiment like in a bar with a very long flight path using ultra cold neutrons, your sensitivity skyrockets just because then you have a lot of time. The neutrons have a lot of time to. So, but I was just mentioning that by default, that's not what we're doing yet. We're producing those cold neutrons.
Okay, thank you.
I see there is a question online from Thais.
Hi, good morning. First of all, congratulations for your work. I would like to ask, I don't really get the idea of of reconstruction neutron. The first option that you showed, you had. Can you listen to me? Yeah. Oh, yes. That's good. You had the option of yes, this one. You have the option, the first option of regeneration. I don't really get how this would prove that.
How this would work?
Yeah.
The reason why this can work. So the idea behind it. Sorry if I was I was a little bit fast. The idea behind here is simply that neutron would split spontaneously if you have, if nature allows it to this sterile neutron or sterile antineutron. And since it's sterile, it does not interact at all with the beam dump stopper that is put here. So when this happens, if this happens, then it's, if you imagine that you have a sterile neutron here, it just passes as this being proper didn't exist at all. So at this point, when it reaches the other side, it's still a sterile neutron. Of course, if it does not flip back to a neutron, then you're still not going to see anything. So the assumption here is that it flips once, then it flips twice, and when it flips back to a normal neutron, then you're able to detect it, because then you can count it. Of course, the neutrons themselves, the normal neutrons, the standard model neutrons, they were stopped, right? They should not reach this at all. So whatever you're counting is very difficult. So whatever you're counting on the other side must be either, I mean, of course, as I said, you have to control the backgrounds. I mean, it cannot be, it's not going to be the first neutron that you see on the other side. Oh my God, I discovered the dark sector, everything's good. So you have to a very good control of your back. But when you, and of course, I mean, you are scanning the magnetic field. So it's also not that you are doing this as you would see, that you turn your equipment and you're just waiting for the flux to go down. That's not what you do. You have to, you know, to control the magnetic field, and then the decrease that you have in the flux has to be significant. So that's how this works. That works.
Mm-hmm. All right. Yeah, I was wondering if you had any number less than the initial neutrons that you had, maybe there were any other mechanisms that could lead to this difference.
You're talking about backgrounds, or sorry, mechanism. I mean, let's try to answer this two ways. I mean, the mechanism itself, that means how this happened. That we cannot probe in this sort of experiment. This is pretty much like the T-2 experiment. So you're not able to tell, okay, what is the model? What is that? The mechanism itself, you're pretty much blind to it. What you can tell is that it happened, and then that will drive activity in, you know, collider experiments, in, you know, all over the place. I think if you were able to detect it.
Mm-hmm. Yeah. All right. Yeah. So if the counter were any difference than what you were expecting at with the absence of dark matter, then it would be dark matter. It couldn't be anything else, could it?
Well, I don't think that you would able to tell this with any confidence, because even here, this is again this sort of what you're probing here is the mediators. I mean, well, knowledge is not important, but what's important is that if you observe something here, is that whichever particle, you know, whichever particle was produced, it had, you know, by definition, it had to be sterile to the beam zone. So it didn't interact. So that is by definition what happened. Sterile particle fits into, oh, that's a very broad question. It's probably fits a lot of different models.
Yeah, sure. All right, thank you.
Yeah, we can discuss, of course, continue the discussion during the discussion session, and we go for the next question.
Thanks for the nice presentation. It was very clear. I have, so this is very different from high-energy physics, because your neutrons are very slow.
Yeah.
So one question I was, so this difference between the bottle and this is very interesting.
It's not my turf, but okay. Yeah. We're gonna go there.
Well, yeah, but what I was wondering, your neutrons are very slow. Yeah. Of course, they're not at rest, but in that case, it's not possible to try to measure the photon. Maybe I missed the last part of the talk. That's what we are talking about. Because okay, you plan to have a detector for the anti-neutron, which is also going to be very slow, I guess, because it's the same.
Very slow,
but then when the neutron is passing by, you could also see the decay, right, of in this dark matter in the photon, or not.
Yeah, but I mean, I think that's basically what you could, in principle. I mean, that's what I said. The detector is built thinking about a signal for an anti-neutron. But in principle, yes, you could, and you can observe radicates, but how sensitive you're going to be compared to experiments that to large volume experiments, that is a question that is not clear, and that you need Monte Carlo simulations to actually be, to be sure that you can do something that is competitive. So you can definitely see it, but be competitive. Yeah.
No, I guess I understand.
Yeah.
And maybe one last question is about the neutron detector, this helium thing that you presented. What is this something that it's already being that's something it's used already in the
these are detectors that exist. This sort of detector. I mean, we have a whole working group for working with this. So but this for detector A. This detector B, no, not as far as I know. I'm not the neutron detector person, but this is I don't know. People are the experts on neutron detection. They are discussing what to do basically.
And that's one of the points is that you like to have a big rate of neutrons, and that's something that probably will
the
10 to the 12
just increases probability. I mean, if you want to have that is just like playing the lottery. I mean, you want to have more tickets so that you're able to to win. But that's basically that's a statistical argument in this respect.
Thank you. More questions? Okay, I have one question, a general question. So the spallation source is like a multi-purpose source, and you have this nice set of, actually there's several neutron dark sector experiments, right?
Yeah.
Is there an experiment to produce neutrinos to make a neutrino beam from the spallation source?
Yes, there is a proposal which is called a neutrino superbeam, which they want to put a far detector. I don't know where in, I forgot where, but I mean, there is a proposal, but it's a very ambitious proposal of producing this neutron beam because it requires some modifications to the DSS standard accelerator, which is kind of expensive. So, but there is a proposal to, and this would be actually, I mean, would be a fantastic experiment that would be very sensitive, but CP violation. This is one of a big proposal. So Heidemann and Barr in terms of this. So I could say this. I mean, there is a paper, white paper that we produce, and all the fundamental physics at the SS that we put in the archive, that I put in the archive, I don't know, in December last year. That is an overview of all the fundamental physics that are planned. Not all of them will see the light of day, but I mean that they are planned, and there is a bunch. I mean, even coherent neutron scattering that I think that you were a bit involved. Right. Well, I was.
Yeah, that's what I'm asking.
Yeah, exactly. So there are proposals actually even for this experiment as well. Yeah.
Cool. Okay, more questions online? Here, yes, one question in the back. So also, please introduce yourself so that people meet.
Hello, my name is Igor, and I have a question. When you look for dark matter in the collision by the end of your lecture, what is the scale of mass of the dark matter particle you are expecting?
I think that the answer to this is I don't know, in the sense that here, I don't know. We're probably I can say you that I can tell you this, that we are far below the gut scale. That's for sure. So in this sort of things, but what kind of mass we're going to probe here, since I actually don't even know if this is going to work at all, it's very. I prefer to say nothing because we have not. This depends on really. This really depends on any physics that you think about, in this case, being favored by a free neutron physics. If it is anything that bound neutrons can do as well, or they're going to do better than us because they just have this massive, detectors with that massive volume detectors. So we're not going. So that's, yeah. I was thinking about whether or not to say a lot about this because this is, work in progress. But yeah, I don't know.
Thank you. Okay, so let's thank the speaker again. If there are more questions, of course, we can discuss on the discussion session. Now we have two flash talks by undergraduate students. So one is recorded, is by Miriam. And the second one is by Manuel, but I don't see him online. Oh, it's in person. Great. Okay, fantastic. So we have we have first a recorded talk and then yours. Então a gente vai começar com a que está gravada e depois você.
Bom dia a todos, eu sou a Miriam Reitz, eu sou aluna da Universidade Federal do Espírito Santo, né? Sou aluna de graduação e faço IC aqui no CBPF, né? Também sou aluna de iniciação científica aqui no CBPF, sob orientação do professor José Abdala Elael Neto. E estou trabalhando em parceria com o João Paulo e o Bernardo, que são ambos alunos de doutorado, né? Alunos do professor Elael aqui no CBPF. Vou apresentar para vocês hoje rapidamente, né, a Dark Side Electrodynamics, que nada mais é do que uma eletrodinâmica estendida na presença do Axion e do Dark Photon, e é com isso que a gente tem trabalhado na minha IC. Então, por que, né, o que nós estamos fazendo? Estamos explorando, então, essa eletrodinâmica estendida, né, com Axion e Dark Photon, para tentar entender um pouco da física dessas partículas em termos da física do fóton. Por que, então, né, nós estamos fazendo isso? Essas partículas, né, essas partículas postuladas, elas ainda não foram encontradas na natureza, né? O Axion e o Dark Photon são fortes candidatos para compor o setor escuro do universo, né? E qual é o objetivo específico, né, desse trabalho? Então, estamos procurando por limites, né? Estabelecer limites, possíveis limites para medidas da pressão de radiação para esse modelo. Queremos, então, encontrar um limite, né, uma faixa ali, um intervalo, aonde a gente pode procurar por essas partículas, né? Procurar pelos áxions e pelos dark photons. Além desse trabalho, né, eu pesquiso, em geral, né, aspectos fenomenológicos da eletrodinâmica estendida, né, além do modelo padrão. Nesse momento, só com Axion e Dark Photon. O modelo, né, especificamente que a gente está trabalhando, é esse aqui, essa lagrangiana, né, onde a gente tem a dinâmica do fóton, a dinâmica do Dark Photon, a dinâmica do Axion, e os termos de mixing, né, que nós temos portais. São através desses portais que a gente vai acessar o setor escuro com luz, né? A ideia é explorar o setor escuro através da luz, através do fóton. Então, aqui a gente tem mixings, né, com Axion Photon e Dark Photon, e Axion e Dark Photon. A gente contempla nesse modelo, né, tanto os casos do Dark Photon massivo, quanto os casos do Dark Photon não massivo. Dessa teoria, né, desse modelo, a gente extrai as equações de Maxwell modificadas para o fóton e para o Dark Photon, né? E a gente consegue obter aqui também, né, os casos não massivos, né, para o Dark Photon não massivo. A gente também tem a dinâmica do Axion, né, provinda desse modelo, e as equações aqui de onda, né, para o campo elétrico e para o campo magnético, tanto, né, para o campo do fóton quanto para o campo do Dark Photon, né, o campo eletromagnético do Dark Photon. Então, basicamente, né, desse modelo, a gente vai extrair tudo que é necessário para fazer um cálculo analítico da pressão de radiação, né, a gente vai obter ali o tensor energia-momento, a gente vai obter, né, do tensor energia-momento vetor de Poynting, a gente vai ter que linearizar esse modelo, e para isso a gente propôs, né, então, um background, né, um campo magnético de fundo, um campo magnético constante de fundo, para a gente poder linearizar a teoria, e uma vez a teoria linearizada, a gente obtém uma solução em ondas planas, obtém as relações de dispersão e faz, por fim, né, o cálculo da pressão de radiação, aí, na esperança de obter esses limites. É isso que a gente tem feito, né, nesse projeto de pesquisa. Agradeço ao CBPF, à UFES, ao CNPq. Caso alguém queira conversar, entrar em contato, pode ficar à vontade, que a força esteja com vocês, beleza? Tchau, tchau.
We can clap, although she's not here. Okay, so I don't see, Miriam would try to connect, but she's had some problems, so I don't think she's online. So we don't take questions. Then we can go to the next talk. Yes, by Manuel Vicente de Souza Filho on the Brans-Dicke-Rastal theory.
Bom dia, sou Manuel Vicente. Eu vou fazer uma apresentação em português mesmo, porque meu speaking eu ainda não estou tão confortável para apresentar um trabalho, mas cosmologia na teoria de Brans-Dicke-Rastal trata-se de um trabalho de iniciação científica que ainda está em andamento, estamos obtendo resultados satisfatórios até, tá? O meu orientador, o Thiago Caramês, ele é da UF de Pádua, eu sou da UF de Volta Redonda, tá? E qual é a nossa motivação? É o modelo lambda CDM, né? Embora esse modelo, né, o modelo padrão da cosmologia, mesmo que ele seja bem sucedido, né, tem que se mostrar bastante sucedido em descrever o modelo, o universo observável, trazendo explicações efetivas sobre a expansão cósmica e a dinâmica de formação de grandes estruturas, ele pressupõe a existência de duas substâncias exóticas que a gente não conhece muito bem ainda, que é a matéria escura e a energia escura. Né? A matéria escura, 30%, compondo 30% do universo, e a energia escura, 70%. Né? No século XX, ele foi demarcado por diversas tentativas de teorizar algo que fosse além dessas substâncias exóticas e que pudesse substituir elas por outros graus de liberdade. Então, na década de 60, nós tivemos a teoria de Brandi, e em 72 nós tivemos a teoria de Rastal. Tá? A teoria de Brandi trata-se de uma teoria escalar tensorial, ok? E a teoria de Rastal, ele vai... É uma teoria em que os aspectos conservativos usuais da relatividade geral, elas são substituídas por uma relação fenomenológica, tá? Então, vamos lá. Então, qual é o objetivo? O nosso objetivo é obter um sistema de equações diferenciais não lineares fortemente acopladas, que vai descrever a dinâmica cosmológica da teoria de Brandi-Rastal, e em cima desse sistema de equações a gente vai fazer uma integração numérica realizada em Python. Com essa integração a gente vai obter os resultados e comparar com os dados observacionais. Né? Além disso, a gente pretende também obter soluções analíticas sugerindo lei de potência, que vai ser agora o nosso próximo passo, né? E verificar as condições impostas pelos parâmetros livres da teoria. Brandi tem um parâmetro livre, Rastal tem um parâmetro livre e Brandi-Rastal tem um parâmetro livre. Tá? De modo que o nosso parâmetro de densidade, que é o ômega φ zero hoje, né? O que é esse ômega φ? Ele vai justamente substituir a contribuição da energia escura. Né? Então, o que nós queremos é que ele seja 0,7 hoje, compondo 70% da energia no universo. Né? Bom, teoria de Brandi, eu não coloquei as equações, mas a teoria de Brandi trata-se de uma teoria em que a gente vai substituir a constante gravitacional de Newton por um acoplamento gravitacional dinâmico φ, tá? E o parâmetro livre dessa teoria é um ômega, que dentro do formalismo PPN, né, que é o formalismo pós-newtoniano parametrizado, o ômega tendendo a infinito, a gente consegue recuperar resultados da relatividade geral. Eu estou fazendo um ômega tendendo a infinito, a gente consegue trabalhar com as equações generalizadas de Einstein e obter um sistema de equações diferenciais que vai descrever o modelo de Brandi. Tá? Teoria de Rastal. A teoria de Rastal trata-se de uma teoria em que os aspectos da relatividade geral elas vão ser violadas no espaço-tempo curvo. Né? Então, a gente consegue descrever um tensor energia-momento em função de um tensor de curvatura de Hit. Tá? E o parâmetro livre dessa teoria é um lambda. Um lambda que, quando fixado igual a 1, dentro de um formalismo PPN, por que igual a 1? Porque dentro do formalismo PPN, a gente consegue recuperar os resultados da relatividade geral. E a mesma coisa, a gente utilizou as equações generalizadas de Einstein para a teoria de Rastal e obtivemos um sistema de equações que descrevesse a dinâmica cosmológica da teoria de Rastal. Tá? E aí, conjugando ambas as teorias, nós temos a teoria de Brandi-Rastal, tá? Que é uma teoria que vai obter, né? que vai carregar os aspectos da gravidade, né, o acoplamento gravitacional dinâmico e os aspectos não conservativos da relatividade geral, vindo de Rastal. Né? Então, a partir dos resultados, né, a partir das equações generalizadas que nós obtivemos, das equações generalizadas de Einstein, a gente consegue, né, obter o sistema de equações diferenciais não lineares fortemente acopladas, que vai descrever a dinâmica cosmológica do modelo de Brandi-Rastal. Né? E aí, através desse modelo, né, a gente vai fazer a integração em Python, a gente vai pegar os parâmetros livres da teoria, fixá-los, ver o comportamento, ver quais são as condições impostas, né, de modo que a gente consiga obter um ômega φ que seja justamente 0,7. E nossos resultados, a gente apanhou, na verdade, muito para obter o resultado efetivo, mas está aí, semanas atrás, esse resultado. Isso aqui é um gráfico do parâmetro de Hubble por redshift, né? A curva preta é o lambda CDM e a curva vermelha é o que nós obtivemos. Né? Então, a gente conseguiu, através de Brandi-Rastal, recuperar os dados da relatividade geral, que está muito próximo. Isso aqui se trata de um trabalho original, né? Não está presente na literatura. O que nós temos na literatura é uma solução analítica, né? Mas a solução numérica a gente não tem ainda, então trata-se de um trabalho original. Tá? Então, a gente teve que fixar certinho, né, os valores iniciais, né, e os parâmetros livres. Tá? E agradecimento ao CNPq e muito obrigado. Né? Essa é a minha experiência. Muito obrigado.
We have time for questions. Temos tempo para perguntas. Alguma pergunta para o Manuel?
Obrigado, Emanuel. Pergunta no último slide, é um ajuste, desculpa, é um ajuste? Não.
Tem ajuste.
Então, de onde tirou os parâmetros?
Não, realmente é um ajuste. Eu pensei que fosse um ajuste do gráfico, né? Mas sim, é um ajuste. Os parâmetros a gente foi tentando, né? Na verdade é o seguinte, esse lambda ele tem que ser igual a zero, né? Dentro do aquele lambda lá, ó, isso aqui é o parâmetro livre da teoria de branquinho cristal, tá vendo? Esse é o parâmetro livre, ele tem que ser igual a zero, porque dentro do PPN, né? Dentro do formulinho PPN, do branquinho cristal, a gente consegue recuperar.
Lambda é fixo em zero, então.
Exatamente. Então a gente teve que ser próximo de zero. Na verdade existe uma relação, né, entre lambda e ômega, tá dentro do código, que a gente teve um trabalho, um vínculo observacional que existe entre lambda e ômega, e aí a gente conseguiu ajustar o ômega e lambda para que a gente conseguisse representar que
Sim, mas é um ajuste, você minimizou um Q quadrado?
Não, não fiz isso. O que eu estou falando de ajuste aqui trata-se apenas de a gente foi tentando valores próximos do que a teoria diz, entendeu? Mas no gráfico em si não tem nenhum ajuste linear, nada. Quadrático, não existe aqui. A gente não está fazendo.
Mas seria melhor, né? Fazer.
Bom, então, no início, né, que a gente estava obtendo resultados não efetivos, a curva, na verdade, ela tava vindo aqui assim, ó, bem longe mesmo, sabe? E aí passou pela cabeça fazer um ajuste, mas não precisou. Não precisou. Talvez, assim, está em andamento. Talvez a gente faça, né? Um ajuste linear, mas... Não, tudo bem.
É o famoso chi-by-eye. Chi-square, que seria a minimização, mas no olho, chi-by-eye.
Isso, foi exatamente isso.
Alguma outra pergunta? Pergunta online, Thaís?
Olá, boa tarde. Bom dia, né? Bom dia. Esses dados que você utilizou foram de onde?
Bom, da curva, lambda CDM, é do Planck.
Os dados do parâmetro Hubble.
Do Planck. O lambda CDM aqui, a curva preta, foi do Planck.
Não, os pontos.
Sim, já.
Os dados.
Observacionalmente, pelo Planck. E aqui nós temos aqui os pontos, aqui os pretinhos são os pontos, e as barras de erro.
De que catálogo?
Não tem aqui, mas se quiser eu mando. A gente tem um catálogo sim, nós temos todos os pontos que foram utilizados
Mas foi o quê? Foi supernova? Foi...
Acho que a pergunta, deixa eu tentar ajudar. Eu acho que a pergunta é qual é a fonte desses números, qual é o paper.
Isso, obrigada, isso.
Mas está entre as referências. Na verdade, está numa apresentação, na verdade, num paper escrito pelo professor Thiago Roberto da Porta Caramês. Ele escreveu um artigo de branquinho cristal, trabalhando com a parte teórica, né, digamos, para obter as soluções analíticas, né? Então, foi obtido através desses artigos, tá? Eu não sei exatamente qual aqui agora, mas se quiser, eu posso mandar para contar.
Uhum. Ok.
Obrigado, vamos agradecer.
Obrigada.
So now we go to the discussion session. So we have time for discussion, and I recall that the discussions are not recorded, so even more free to ask questions. Don't be shy. Questions are welcome, of course. Also, so okay, let's get the first questions to all the speakers in the morning. Yes.
Thank you. I have actually two questions. One is for Pedro.
Nelson, you there?
Hello.
Hi. Do you want to try the slides?
Can you hear me?
Yeah, I can.
And the microphone is not, it's not connected or it's off.
I can hear you.
Hey, Martin. I can hear you guys. Wait, is it? No, it's me. It's me. Sorry. Wait, I'll put my headphones on. Hello.
Hello? Can you
Yeah,
hear?
now I can hear. Yes, thank you.
Do you want to try the slides? See, is everything okay?
Okay. So will I share my screen then to present?
Sorry?
The presentation is via share screen. So do I share my screen to?
Yeah.
Okay, great. Excellent. Want me to start sharing now, just to be ready?
Okay.
Yes. Can you see it? Can you
Yeah.
see my screen? Good.
It's on the phone screen. We can see it perfectly.
Excellent. Thank you.
Great.
I have lots of birds here, so it may be a bit noisy.
minutinho. Um minutinho. All right, so welcome back everyone to our afternoon section. So now we have the talk, Consequences of Primordial Black Holes as Dark Matter by Nelson. So Nelson, you have 40 minutes and I'll let you know when you have 5 minutes left, okay?
Excellent, thank you very much. Can you hear me well?
Yeah, perfectly.
Yeah, okay. So can you see my pointer? I'm moving it around the whiteboard.
Yeah,
okay. So thank you very much. Thank you for the invitation. This is really nice to be able to talk at this first Dark Matter meeting in Rio. What I'm going to talk about is work that I've been doing in collaboration with Federico Estasis, Patricio Colasso, and Ana Durant in the institute here at IATE in Córdoba, in Argentina. But we've also been, the results I'll show are also done in collaboration with Catalina and Patricia from Universidad Católica de Chile, Juan Magaña, Ignacio Araya, Joaquín Sureda, and Marcelo Rubio from other institutions. So I've recently moved back to Argentina, so my work is being mostly supported by a grant from the Raíces program in Argentina. And what I want to talk about today is first tell you a bit about the fact that primordial black holes and dark matter particles are depend a lot on the details of inflation and the extensions to the standard model of particle physics. So we learn things about these two things from studying dark matter, right? And of course, I'm going to concentrate on primordial black holes. And in particular, we will see that we have now a framework to talk about primordial black holes of mostly a single mass that is related to the way in which these black holes form. So it's actually quite nice. Then I'm going to move into the consequences of primordial black holes being dark matter, showing first feedback from accretion onto primordial black holes, accretion of baryons within galaxies onto primordial black holes, and how can this affect galaxy evolution, right? And also we'll see from the work with Patricio that even just modifying the initial conditions so that primordial black holes exist can change the abundance of low mass dark matter halos, and this is something that we hope to be able to measure in the next few years, for example, with the Rubin Observatory. And finally, we found that primordial black holes should hold electrical charge. So another consequence is that there will also be feedback, energetic feedback from the interaction between the dark matter made of charged primordial black holes and baryons in galaxies. So let's start. So we know that inflation has no observational evidence yet, but it provides solutions to several problems like flatness, amplitude of fluctuations, and horizon in cosmology. So it's quite interesting. We know that dark matter is needed if we want if we want general relativity to be the definitive representation of gravity. We know that there are extensions to particle physics that provide several candidates for particles that could behave as dark matter, as we saw in several of the talks today and yesterday. And a more classical candidate than particles from extensions of particle physics theory are primordial black holes, and these have been proposed as possible as part of the matter in the universe since the late 60s. And there, in the last few years, maybe in the last decade, there are several advances in inflation that are actually bringing them back into the attention, right? Because they would be formed if inflation is modified in some different ways, right? So dark matter studies are actually really interesting to help people understand inflation and also constrain extensions of particle physics theories. And you've seen talks about different parts in different proposals for dark matter particles, axions, ultralight dark matter, fermionic, bosonic dark matter, and so on. And here you can see the range of masses, right? This is a mass in electron volts from 10 to the minus 21 all the way to 10 to the 12 electron volts, for example, for weakly interacting massive particles. And primordial black holes basically lie at the very, very high mass end of particles, right, of objects with very high masses. And there are different ways to try to detect this dark matter directly, because of course the only evidence that we have is astrophysical, as I was mentioned earlier today, or via gravitation, right? So let's concentrate then on primordial black holes. These black holes were first proposed by Seldovich and Novikov in the 60s. They could form when, in the very early universe, as soon as an overdense region enters into causal contact, it can form an event horizon surrounding it and basically produce instantaneously a primordial black hole. And the mass range that these objects could have is basically all the range of masses that we can have in the horizon since the end of inflation until today. I mean, until at least, for example, the end of radiation domination, and that gives you very, very wide range of masses from 10 to the minus 38 solar masses to 10 to the 15. Note that all these masses would still be present today, because, for example, primordial black holes could evaporate via Hawking radiation, in which case this range here, instead of going all the way down to 10 to the minus 38 solar masses, would be limited to 10 to the minus 20, right? And of course, this should not be confused with astrophysical black holes, which are not useful for dark matter, because we know that we have dark matter since at least the formation of the cosmic micro radiation. So we didn't have stars then, so these astrophysical black holes are not good candidates for dark matter in that sense. Right. So apart from this channel of formation, there are also other ways, right? I mean, the channel from Seldovich and Novikov was basically thinking about an overdense region that collapses. But I mean, just to show one exception to this, there's a recent paper by Saulo Carneiro in 2021, who showed that at the very early universe, right after inflation, the high energy tail at a good scale of roughly, for example, 10 to the 17 electron volts, can produce Planck mass primordial black holes by collision of very energetic particles at those times, in such a way that these primordial black holes are extremal and therefore do not evaporate via Hawking radiation, have essentially zero temperature, so they're stable. And the fact that we can only think that this can be produced in a very high energy tails also allows for there to be just enough mass on these primordial black holes so that they can be an important part of the dark matter today, right? I mean, the energy density drops off more rapidly during radiation domination by an extra factor of 1/8, the scale factor of the universe. So we know that their abundance has to be very, very small compared to the total energy budget at the end of inflation, right? And very recently, I mean, this is a paper that just got published a couple of months ago with Ignacio Araya. We show that this can also be extended to electron or positron collisions, which can produce Reisner-Nordstrom extreme and primordial black holes, which would also have a charge and would also be stable under evaporation. And of course, in both cases, the spin needs could be large. In the case of charge, the charge will provide extremality conditions so that these primordial black holes don't evaporate, and it's needed for the case of a collision of zero charge particles. In the case of Saulo Carneiro's proposal, and let's go into there's a bit more detail into the case of formation of primordial black holes by collapse of overdensities. So let's go over this a bit. There are even full relativistic simulations of this process, when a patch that is originally overdense comes into causal contact and it holds an overdensity that surpasses the critical overdensity for collapse. This is in physical terms, right? There's no linear theory here, right? So the horizon energy is basically the energy of the patch, and the fraction of that collapses to form the primordial black hole, right? This takes into account the excess mass within the horizon due to the overdensity, and this gamma parameter is basically fit and is close to 1, right? The density contrast for the formation of primordial black holes is somewhere between 0.3 and 1, depending on how it is calculated. So we can basically approximate it to 1 roughly within order of magnitude calculation. Now, if you look, for example, at the measurement of the primordial power spectrum from Planck, right? I mean, we only see a fraction. I mean, only on the very large scales we see the primordial power spectrum, and that primordial power spectrum has a power index that is slightly lower than 1, giving some insights on what inflation could have been, right? Because inflation affects what is this power law parameter, right? Which is close to scale free, right? But if that is the all the dependence with scale of the primordial power spectrum, then there will be no primordial black hole formation at all. So if we want to have a collapse, right? So I'm showing here just an example of the lambda CDM power spectrum at redshift 1100. So this is at the decoupling redshift between radiation and baryons. And this is the typical shape affected by what happened within the horizon up to this point, right? So this is not the primordial one. The primordial is basically just power law. This is the one that's measured by Planck. It should continue straight away if there are no modifications whatsoever, right? But for example, at some scale, some inflation models predict that there could be an increase in the power, and also some particular shapes for the inflation, for the inflaton potential can also produce, for example, spikes. So this here is sort of representing like a general shape of a primordial power spectrum for different modifications to, for different predictions from inflation, right? So we have several parameters. There's a scale from which we would have this variation of the power law index of the primordial power spectrum, and it has to be on a scale that is not observable, because we know that it's quite consistent with being just constant throughout quite a large range of scales, even from CMB experiments. It's taking into account the expected effect from the transfer function, right? But still, one thing that we need to take into account, what we mentioned before, is that the mass of the black hole is basically all the energy that's contained within the horizon that collapses, or perhaps only a fraction will collapse and form the black hole, because we need a very specific fraction of the total energy density at the moment that the black holes form very, very early within the radiation domination, so that they will be only a fraction of the dark matter today, right? Because of the extra factor of dilution during the radiation domination. So, right, so we can explore all these parameters, the scale from which we have a change in the power law index, the second power law index, the scale at which we have the spike, the amplitude of the spike, and so on, right? Which are basically shown here. So once we have this power spectrum, then one can think of the power spectrum that we have here as a linear theory power spectrum, and then we can use a formalism called pressure sector, which can turn this power spectrum into an abundance of objects that collapse once a fluctuation surpasses a given critical density threshold. But in this case, if it is a linear theory power spectrum, it will be it doesn't necessarily have to be the same as the collapse threshold in physical coordinates. And this is something that needs to be taken into account. So what one does with the pressure sector formalism is take a power spectrum, turn it into a variance of the density field, then use this to work out a peak height, which is simply, and you already need to figure out what your collapse over density is, divided by this variance to obtain how rare the peaks that you will be looking at are, right? And then turn this simply by change of variables into the mass function for the objects that you expect to form from these fluctuations, right? So this power spectrum then is a primordial power spectrum with the modifications from whatever model of inflation you want to include. If you use this formalism, then you need to make sure of a couple of things so that it is actually reasonable to use it. The first one is that the ratio between your critical density over density for collapse and the typical over densities that are involved in the collapse are of the same order of magnitude, so that there's a strong relation to your power spectrum, right? And why do we ask for this? Well, if your collapse density is too small, right, it's basically 0, then there's actually, it's basically saying that all over densities, no matter whether they're very small or not, will collapse. And there's a relation to the shape of the power spectrum, but there's really no need to use a projective formalism in a sense, right? Because you're simply saying transform the power spectrum into mass function, and that's it. And on the other hand, if the collapse threshold is too high, then your process is fully stochastic. And again, it will basically be a Poisson distribution rather than something related to the actual power spectrum. You will lose information about your power spectrum if this happens. So when we work with the projective formalism, we're careful to check whether our solutions are close to this case where there is a strong relation to the power spectrum. And then the other thing is that we want to target a density, a dark matter density today. So we basically have to have a fraction of the dark matter that collapses, of the energy density that collapses into dark matter. And that is basically the ratio of the density of primordial black holes and the total energy density at the scale factor where the formation occurs, right? So if we think that only the central part collapses, then we will define this F sub m as that ratio in particular. But if a fraction of all modes collapse completely, then it's a different thing, right? This is quite stochastic. It's a very, very tiny fraction of all the patches that satisfy the overdensity condition for collapse will actually collapse, right? So this parameter can actually be anything between this required parameter and 1, right? It's something that one can explore continuously, but we basically just look at one or the other to see the two extremes. Things don't change too much, but it's important to take that into account. And finally, what sets the conditions for a particular patch to collapse? This is something that happens, for example, during I don't know, some phase transition, like in the case shown here, where bubbles expand, and at the borders of the bubbles, you have a buildup of energy density that's basically imprinted there, and it waits until it enters a horizon and forms the black hole. In that case, we'll basically be saying that all the initial condition for the formation comes at a single scale factor, fixed conformal time condition. And the other one is that we simply have a power spectrum that comes from inflation, and the collapse will occur whenever that fluctuation that was not a causal contact after inflation comes into causal contact and basically realizes that it has to form the event horizon and form the black hole, right? So the difference here is that the evaluation of the amplitude of fluctuation is made at the moment that the linear mode enters a horizon, instead of doing it at a fixed time, fixed scale factor, right? So there's also two options. We don't know really what happens. We don't know what sets the initial conditions for primordial black holes. So what we're simply doing is setting up all the parameters that we can basically modify or play with as we look at different mass functions. And finally, what we also assume is that the evolution of the energy density fluctuations outside the horizon has a very specific form, right? But we know that wherever you have a peak that will satisfy the condition for formation, that peak will evolve as if it is just a position, right? So it evolves as with 1 over the volume, and it doesn't evolve as the energy density of the universe. That's another assumption that we make. And with that, as you see here, we have several parameters. We have all the parameters of the primordial power spectrum, the energy content that we will have with a fraction of the matter, the energy density in primordial black holes, and then the time of imprint of linear fluctuations for primordial black hole formation, and whether a fraction of the patches or a fraction of each individual patch collapse to form a black hole. It's a lot of things, but we can work with this, and with this we can actually produce mass functions where we have on the x-axis, of course, the mass of the primordial black hole and the abundance on the y-axis. And these mass functions will look a little bit like this. There will be a power law that will have a drop-off at some characteristic mass, and can also show a spike, right, at some point. The community quite often looks at, for example, constraints on the abundance of primordial black holes by assuming that they all have a single mass, and that's actually quite a good approximation to some cases of the actual mass functions that one can calculate from primordial power spectrum. So here's an example, no, 3 examples rather. So these are mass functions here on dashed lines that correspond to primordial power spectrum without spikes, but with a tilt, a blue index of the primordial power spectrum at very large wave numbers, basically at very small scales. And in solid lines, you have examples with spikes. And these spikes in particular contain about half of all the matter within primordial black holes in the universe. And as you can see, by the orders of magnitude spanned by the abundance of these objects, that when you have a spike, you can very well consider your distribution of masses to be almost monochromatic or log normal, very, very, very tiny, okay? So these are different shapes of the mass function. One can turn, for example, constraints on monochromatic mass functions into extended distributions from power spectra with no spikes, only with blue indices. And right, and then what we need to do now is to say, okay, if we have these primordial black holes everywhere, how can we make constraints on their abundance, right? So we need to know how many of them are there and where do we find these primordial black holes at any redshift and also at present, right? So here, there's also a consideration that's actually quite nice. And I mean, it's very simple. Primordial black holes form from primordial fluctuations, but those fluctuations evolve after the primordial black holes are formed, because they form as soon as the fluctuations enter the horizon, right? But every fluctuation that doesn't turn into a primordial black hole evolves within the horizon in the way that we know they do, right? Black holes already formed act as dark matter, so we know how to treat them within the horizon. But what is happening in essence is that this evolution during the radiation era and down to recombination will modify, by orders of magnitude, the small scale power, right? So what happens is that the final power spectrum that we have, that we measure at the CMB, is completely independent. The fluctuations are completely independent from the primordial ones that gave rise to the formation of primordial black holes. And galaxies form from the latter ones, right? So what we can do is, and we have to do, is assume that starting at decoupling, or even earlier, right, within the horizon, the primordial black holes are randomly distributed within the horizon. And dark matter halos, or galaxies, equivalently, contain random samples of primordial black holes. So they're taken randomly from whatever distribution of masses and spatial distribution we can have, right? Then via astrophysical processes, they can move around. And for example, primordial black holes, the ones that are more massive, can sink to the center of the halo, but not initially, right? It will be randomly distributed, regardless of their mass. So with this, people do a lot of constraints on the abundance of primordial black holes. And here we have some examples. This is a figure taken from CAR 2020, where there are different sources that tell you what is the maximum fraction of mass, of the dark matter mass that we can have in primordial black holes. It can be very low, 10 to the -9, or it can be 1, where all of the dark matter can be in primordial black holes. There are some windows, for example, here around 10 to the -10 to 10 to the -15 solar masses on the top axis and grams in the bottom one. And there's also another small window here because some of these constraints are disputed currently, right? And by the way, the low mass constraints are due to evaporation via Hawking radiation. Those do not apply to extreme and Planck mass primordial black holes formed via collisions, right? Those could still be, are good candidates for 100% of the dark matter. They basically escape these things, right? And one interesting thing is that when you make mass functions from primordial power spectrum with spikes, this window here becomes quite open, right? As you can see here, this is again fraction of mass in primordial black holes, the function of the spike mass in solar masses, and the fraction is 10 to the -7 here, but it jumps suddenly to, it doesn't matter if it's larger than 1, it basically says that all of that matter can be in primordial black holes. And also the window around 1 to 30 solar masses is also open when you take into account the press-sector formalism and realize that there are also primordial black holes of other masses along with the single mass of the spike. Right, so let's look at more consequences then that one expects from primordial black holes. So primordial black holes within galaxies, they're randomly distributed within the halo. They are not supported by pressure, so they're basically collisionless. So they are completely independent dynamically from the baryons, which basically are pressure supported and then evolve via radiative cooling, right, to form the galaxy disk, stars, and so on. Right? So what happens when primordial black holes, which are zooming through the galaxy, acquire some baryons and start to produce accretion disks? Accretion disks produce a luminosity that can actually heat back up the cold gas that is trying to form stars. So this provides actually quite an interesting feedback mechanism that takes a cold gas from the galaxy that's about to form star, it's basically reheated up back to the hot phase via the emission of the baryons that are being accreted to the primordial black holes that zoom through the galaxy, right? So this is work in progress. This is part of Catalina Casanueva's thesis in Católica in Chile. And what she's finding is that if you have no primordial black holes, the temperature, the final temperature, is basically as low. Cold gas is everything below 10 to the 4 Kelvin, right? The number, the temperature. So if you are within the shaded region, then you're fine. Your galaxy can form stars, and galaxies will exist, right? So as soon as a fraction of 33 solar mass primordial black holes, being the total part of, being the dark matter, as soon as that fraction goes above 10 to the -3, then the temperature of the gas becomes too high and it would not be able to form stars. So we sort of have a region of the mass of primordial black holes, right, around 1 solar mass, that it can be removed via feedback, and it can basically be lowered down to 10 to the -3. That would only leave the low mass end if we can confirm this properly, right? This is work in preparation, just news, hot off the press, so on. And the allowed range that we will still have is, of course, the window of very low masses for the spike of the primordial power spectrum. So what else can we do, right? So this is the case of the primordial, of the mass function for the primordial black holes with the spike at 10 to the minus 14 solar masses. You see, there are a lot of higher mass black holes, but which are much, much less abundant. So the most important ones are actually these ones here that contain half of the total mass, right, in primordial black hole. So what else can we do? We can actually take a look at what is the effect on the structure in the present-day universe produced by the modifications to the primordial power spectrum that allow these primordial black holes to form. These primordial black holes are too small, so they won't make an actual modification to anything that we can measure today directly, especially into the structure, right? But the blue tilt of the primordial power spectrum index changes also the slope of the power spectrum at late times, right? This is after recombination. So you see the blue tilt also affecting very, very small scales, right? This power spectrum as a function of wave number, small scales on the right. And you can evolve this and compare it to, for example, the linear evolution that you expect for this spectra here, using numerical simulations. This is what Patricio Colasso has been doing. And he can actually see that even on the very nonlinear regime, you still find differences. And those differences can be seen, for example, at redshift 10 in the matter distribution in these simulations. So the one on the left is just lambda cold dark matter, no blue tilt. The one on the right is lambda cold dark matter with a blue tilt that will make the dark matter be primordial black holes of, for example, 10 to the minus 14 solar masses, right? So you see that the structure is actually quite different. And in particular, there are tiny things that we cannot see here on the left, right? The numerical simulations run with gadget 4, right? And one can actually evolve these simulations, for example, down to redshift 1. And now look at the mass function of dark matter halos. So this is not abundance of primordial black holes. It's abundance of halos that can host stars at very low redshift. And what you can see is that as you modify your primordial power spectrum to produce black holes, primordial black holes, the abundance of 10 to the 8 solar mass halos increases by up to factor 3. This is quite interesting because one can actually make measurements of strong lensing in galaxy clusters, especially if we have, when we get to have thousands of these observations, strong lensing with, for example, Rubin, to make statistical estimates of what is the abundance of substructures of this mass. And that is actually something that has been proposed to also check whether dark matter is warm. Because if dark matter is warm, then they basically become thermally decoupled from the rest of the radiation in the early universe at quite later times compared to cold, earlier times compared to cold dark matter. So that structure only forms from around 10 to the 8 solar masses and up, right? So this is something that we can hope to measure within the next few years. So we don't have a constraint yet, but we have predictions that can be used to put constraints on the conditions for small primordial black holes to be formed. So what else can we do? Do I have time? I have 5 minutes. So what we can do is we can also look at feedback effects in galaxy formation from charged primordial black holes. For example, like the ones that could possibly form from high energy collisions right after inflation of charged particles. So what type of charge can we have in primordial black holes? So primordial black holes basically form by basically closing a region within the horizon, within the Hubble horizon, with an event horizon of a black hole. So it wasn't in causal contact before. So if a plasma would form, it wouldn't be able to homogenize the charge. So the charge would be imbalanced in different horizon volumes at the early universe, right? We know that we expect to have fluctuations of density, so we can also have fluctuations of charge. That's the reason we should have the same power spectrum, right? So this is actually something proposed by Maldacen in 2020. There could be a magnetic monopole charge because of this that would provide either positive or negative monopole charge to primordial black holes. We found a way to write this monopole charge in Ignacio Araya's paper in 2021 as a function of the present-day abundance of magnetic monopoles today, and find that if we simply put monopoles below the current upper limits for their abundance, they can produce, for example, the seeds that are needed in order to explain the magnetic fields that we see in galaxies today. So only the seeds. This doesn't provide the amplitude of magnetic fields observed today, but we know that the magnetic fields observed today can be basically enhancements of a seed due to dynamo effects in galaxies, right? So since we don't find an excess of magnetic field, we really don't have a new constraint here, but it's quite interesting that this could happen, right? Right, what else? So magnetic charge, okay, let's leave it on one side. What about electric charge? So in the paper by Ignacio, more recent this year, we review the reasons why it is commonly accepted that primordial black holes should hold no electric charge whatsoever. And we indeed confirm that an initial charge, for example, from Poisson fluctuations or via collisions, should be quite rapidly lost. Because they're basically connected to free charges, at least for some time after they enter the horizon. So they should discharge, right? And what would their initial charge be? Well, it's basically something that goes with the abundance of charges at a given time, right? Taking into account, for example, annihilation processes in the early universe and so on. We can actually calculate what this charge would be, or the charge from collisions, right? Which is simply the Reissner-Nordström extremal charge. And but one thing that we realized was that if you have, for example, this is quite interesting, if you have a primordial black hole with a spin parameter, dimensionless spin parameter A, then you can sort of calculate an equivalent magnetic field force at the outer horizon, which has this expression here. This is an exact calculation. And you can take into account the strongest emission mechanism of charges, which is a Schwinger mechanism, which can also be turned into a force equivalent for the process that has this expression here. And you can see these two things are exactly the same for the case of extremely rotating primordial black holes. So if primordial black holes are formed with a high spin, there is quite a strong, there's a possibility that even though they would emit charges, those charges would be limited to the surroundings of the black hole due to the magnetic field from their spin, and from afar they would look as if they hold their initial charge. So because of this, since we don't know what is the expected spin of a primordial black hole, there are suggestions that the spin could be actually quite high. Some of this initial charge could be kept until late times. And the other thing that should also be taken into account is that primordial black holes should acquire charge whenever they're embedded in a plasma. And this is the case of primordial black holes within dark matter halos, or around, in the halos of galaxies today. So just due to repulsion of charge acquired by the primordial black hole and the plasma, surrounding plasma, there's something that is something that we expect. So you can think of, well, how big is this charge? Well, compared to the extremal charge for Reissner-Nordström metric, the charges will be the black line for the case of charge acquired in halos, redshift 0 today, right?
Nelson,
And yes.
Sure. You have only 1 minute, okay?
Okay, thank you. And this blue line here, or light blue, for the initial value from Poisson fluctuations, right? So anything in the gray area is allowed. This here is something excluded from radio observations, for example, for the charge. It's actually calculated for milli-charged particles, right? But since we don't know what the spin is, it should be somewhere in here, right? Okay, so the Poisson charge can be either positive or negative, and the black line is only for negative charges because it can only acquire the light charge carriers, which are the electrons, right? So, I mean, the charge will make changes to the shape of the dark matter halos that host them, even if, you know, they're much, much less important compared to gravity, which, you know, the gravity and Coulomb forces are comparable when you're at the red line, the maximum Reiner-Ostrom charge. So here they wouldn't be so important. But, for example, what happens if we take into account that primordial black holes are not forming at any time? They're not forming a plasma in the universe, so they cannot really homogenize their charge. So dark matter halos that form from these charged primordial black holes would hold the charge. That would also be due to Poisson fluctuations of the number of positively and negatively charged primordial black holes. And in this way, within the window that we have remaining for all primordial black holes being dark matter, we can produce a magnetic field that is consistent with the seed that is required for the observed magnetic field. And not only that, because of the interaction between charges of different types, of different kinematics, for example, we know that there could be a transfer of energy from the primordial black holes to the baryons. And here we have charge, it's a function of mass. If the charge was larger than this blue line, it would disrupt molecular clouds, which are very short-lived. But if they are on top of the blue line, then no galaxies would form because that interaction would basically be enough to offset the cooling that is necessary to form the galactic disk and stars. So we have further constraints here, which basically remove even further the window that we had already removed from feedback from accretion disks. But if the black holes spin rapidly, right, then this is also lower than the blue line, which is the initial charge. So if they spin rapidly, then we would have removed completely all possible windows for primordial black holes, leaving only the extremal Planck mass black holes as possible candidates from the black hole side. So I'll leave the conclusions here and take any questions if there's time. Thank you.
All right, thank you, Nelson. I think we have time for one quickly question. So questions from the audience?
So if I understand well, only the extremal black, after all these tests, only the extremal black holes would be allowed in that very low mass range, right? What is precisely, I mean, in that plot, you have these microlensing constraints from M31 and the Centro lensing, right? These Saya,
yes.
Vinish ones. So where
This
exactly is, right, so you are at the left of the HSC constraints, right?
Yes. So
these
constraints are actually not disputed, right? So these constraints are reasonable. The ones that are still not completely firm, I would say, are the ones from observations of white dwarfs and neutron stars, which are also, I mean, these stars should be basically bombarded by these tiny primordial black holes if they were all over the dark matter, and you would expect to see some observable effects there, but it's not clear whether you know, this is a firm prediction at the moment, right?
Right. And the femto lensing, I would definitely argue
yes.
against. I would say you can discuss. So at the end,
yeah.
Yeah, right. So the question is, on your dashed lines, all this region is still allowed by the analysis that you have shown also. Is that right?
I think so. Let me check more. So this is 10 to the minus 16. So, right. And we are, yeah. So 16 is 10 to the 14 kilograms, right? So the no galaxy formation due to charge, even if we assume that the spin is very, very high, right? It wouldn't be enough to remove that window. Yes, it would perhaps hint that there should be a lower fraction, but of course we don't know the spin of the primordial black hole, so it could, easily be, the charge could be much lower, and there will be no constraint. So this constraint is, only present if the dimensional spin parameter of primordial black holes is 1. This line here.
Okay. So I think you can continue the discussions in the discussion section. So let's thank Nelson again.
Thank you. Thank you again.
Now we have the talk from Gabriel. Gabriel, is that? Você vai ter 25 minutos. Esse daqui é o point. Ah, não, acho que é o contrário. Esse daí passa, né? Okay, so now we have the second talk from the afternoon, and for Gabriel.
Thank you. Good afternoon, everyone. My name is Gabriel Teixeira. I am PhD student at here, CBPF, and my advisor is Clécio de Bon. So today I will talk about a most, I think, fundamental topic, in the sense that most of the presentation here, or some of them, mentioned redshifts in some way, but I will talk about how to obtain these redshifts. Okay, so I want to follow this outline here during the talk. And well, what are redshifts? We can think in, are you listening to me? Okay. We can think in redshift as being a measure that is strongly related to the distance of an object in the sky. In this talk, I will always talk about galaxies, and so we can think in the redshift as being a measure strongly related to the distance of a galaxy from us. And in the local universe, we can think it also related to the velocity of this galaxy relative of us. All right, and the redshifts are actually the redshifts are actually a spectroscopic measurement. So we have to compare the spectra of the galaxy with the no emission or absorption lines of elements that we expected to exist in this galaxy, and we have then we have the relative displacement of wavelengths in the spectrum of this galaxy, and yeah, we have our redshift. So when we measure redshift in that way, we call this redshift as spectroscopic redshift, and this is the most accurate, the most precise way to measure redshifts. Okay, so there is another way to measure redshifts, and we do that using the photometry of these galaxies. So in the photometry, we are not interested in the entire spectrum of the galaxies, but we are interested into the amount of flux of light that pass through specific intervals in wavelength. Okay, and we call these specific intervals bands. And during the talk, I will refer to this amount of flux as magnitude. There is a linear logarithmic relation between flux and magnitude, and we can think in that as being how brightness the galaxy are the galaxies in this band. So when we do that, it's clear that we lost a lot of information about the spectra of the light. So the redshifts that came from photometry are have lower precision when compared to the spectroscopic ones, but photometry allows us to measure multiple galaxies simultaneously, and it demands lower time exposition time, and it can collect data from large areas of the sky when compared to the spectroscopic way. So we have a lot more data in photometric data than the spectroscopic data. So how we can obtain these redshifts? There are two main ways to obtain photometric redshifts. One of them is the template fitting way. And when we are dealing with template fitting, we have to compare the magnitudes that we measured with known spectra of different types of galaxies, and we do that for many spectra. And in the end of the day, we will have estimation for our redshift. And one of the most famous methods of template fitting is the Bayesian photometric redshift. And if you are interested in it, just search about that. It's a reference in the area. And the other way to estimate photos is with machine learning. When we are dealing with machine learning, we have to train a artificial intelligence model. And so we need the photometry to give this model and we need also the spectroscopy to tell this model where we want to go, to tell this model what is our target. So when one machine learning model is trained, once the machine learning model is trained, we can estimate photometric redshift for unknown galaxies in a fast way. Okay, so how machine learning methods works? I will tell you, I will explain it to you with the most basic units in the machine learning. Actually, in deep learning, you can think in deep learning as a subset of machine learning techniques. So what is going on here, that we have an input vector. So we can think in this case as being the magnitude that we measured, and we have a output. In this sense, we can think the output as being the redshift that we want to estimate. So we multiply we multiply each of the components of the input vector by weights. These weights characterize the connection between our input vector with our neuron. The neuron is the most basic unit in machine learning, artificial intelligence. And this model here that I just showed to you in a simple way is the most basic model in deep learning, that is a combination of multiple neurons. Okay, so we have multiple layers of neurons, and each layer is fully connected with their respective neighbors layers. Okay, so we have to multiply each of the components of this vector by weights that characterize this connection, and after do that, we do a summation over all these products, and finally apply the function called activation function. And we can think in activation function as the function that decides what we have to do with this information here and how we will pass this information through the model. Okay, so you also can think in that in a linear algebra way, and realize that here we have a kind of matrix multiplication, and we can see each one of the layers in our model as a vector, and each one of these vectors is given by a matrix multiplication between the previous vector for the matrix that characterizes the connection between the layers, and a activation function applied at each component of this vector. Okay, so in the end we have a output that in this example we can think in as being our redshift, and we have to compute how much the network are wrong. Okay, so we have to compare this output with our target output, what we want to achieve, and in our case the spectroscopic redshift, and we can compute this error in multiple ways, and these ways we call cost function or loss function. Okay, so there is a lot of cost or loss function that we can use, and here is some example that is the mean squared error, and what we want is to find the optimal set of weights that minimize the loss function. Okay, so when we achieve this in an interactive way, we can say that our model is trained. Okay. Here is some examples of activation functions, and well, we could just put the magnitude here and the spectroscope, the photometric redshift here, and compare to the spectroscopic ones, and well, we will have a model that gives to us just what we want. But we also want to compute the error of our own model, and there are many ways to do that, and it's important because, for example, in the weak lensing applications, I required that the redshift are using required that the redshift that it's used have to be a error less than 1%. Okay, so we do that. I'm sorry. We do that with a specific model that gives to us not just the error in your measurement, but an entire probability density distribution for redshift for each galaxy. Okay, so it's very more powerful than just give it to us the redshift value. We can do a lot of statistics here, and it was made after us by Eric Lima and the data of S+ survey, and Class and me are here. We collaborate with this work, and we apply this technique with remarkable difference at the Delphi data. Okay, so what mixture dense networks do? Here, with the model gives to us a set of parameters that characterize our final PDF that we want to achieve. So this PDF here is just a linear combination of Gaussians. Gaussians are PDF that we are all used to deal. So it gives us the linear combination characterized by this set of weights alpha here, and our model not give to us one value, but a set of subsets of 3 values that characterize each one of these components for our final PDF. Okay, so here is a model that we can choose what model we want, but how can we choose the model that we have to put here? Is actually a freely decision, and if the model gives to us this set of parameters, we can choose whatever we want, and we choose for this task here. It's not okay. Okay. We choose for this task the legendary memory units. The legendary memory units are a type of recurrent neural network that is very efficient to deal with time sequence and problems that are time dependent. And here, I think you can see, but we choose this model because we participate on a challenge in around 2020, and we submit a lot of models to this challenge to do a task of classification of galaxy in beams of redshift, not just the redshift values. And months later, with the Delphi data on your hands, we tested all these models that we submitted here into the Delphi data, and the better results were achieved by the LMU model. And we decided to carry on with this model until now. So this is our final network, and it's a combination of LMU model with the dense model. Dense model is just the simplest deep learning model that I showed before. And okay, where the data come from? The data we use come from Delphi Data Release 2, and it covers approximately 17,000 degrees squared simultaneously in the bands G, R, Y, and Z. Actually, it covers more than that, but this shaded blue area have all of the 4 magnitudes here. Okay, so we cross-match this data here with several spectroscopic catalogs to have the spectroscopic redshift to give that to our models, and catalogs that catalogs like Legacy DR9, Sloan Digital, Sky Survey, Hubble Space Telescope, and Arcane Survey. And we had to do some constraints of this data in the photometry parts to guarantee that we are dealing with good quality data. So we made constraints, for example, in the signal to noise ratio, and we also cut faint objects here. Okay, so our final data set had about 1.2 million of objects, and we splitted these objects into a training sample and a test sample. The training sample are the objects that we use to train our network, and the test sample is our objects that the networks will just see once it's be trained. All right, so we can validate our results with the test sample. Okay, this sample here, this data here, were not used to train and to teach the network what it have to do, and we evaluate this after the training process is done. Okay, so to evaluate that, we have to define some metrics, and we divided the metrics into point-like metrics and PDF metrics. The point-like metrics just needs the photos value that was defined as being the redshift value that corresponds to the peak of our PDFs, and the PDFs metrics is just the metric that's considered all of the PDF to be made. Oh, I'm sorry, spoiler. So the point-like metrics we used was the bias is just the difference between the redshift, the photometry redshift, and the spectroscope one. The scatter that gives to us a notion about how our error is scattering around our own median, and it is important also you use it in the literature. And the outlier fraction that gives to us how much of our data of our results can be considered outlier, where outlier is defined by this expression here. And the way we compute the error is just the half of the interval that contains approximately 68% of probability to have our redshift. Okay, so the median bias is the median of the bias. So the PDF metric we used was the PIT metric, and we will have to know that this guy here, each galaxy will have a PIT value, and we have to look to the distribution of pitch values. And this distribution, the shape of this distribution, tell us how much our model is under or overestimating the results, the photometric redshifts, okay? And the odds is just how confident we are that the redshift we say to be is how confident we are in our estimations, okay? So I will show some results. Okay, so here we can see that our model fits the magnitudes into photometric redshifts, and we have some good results here that there is a correlation between the photo Z and the spectroscopic redshift. And here we can see the bias for, I can see all of the objects is less than 0.1, okay? And we can also see that there is a clearly bias here. The most of objects are being overestimating, are under the 0 line in bias and under the x equal y line here in the x equal y axis. Okay. Okay, I'm finished. So here is the point matrix that I mentioned before, and these error bars here are made using a technique called cross-validation. It's just a technique that divide our training sample in different ways and training the same model with different training samples, and give us a error bar, error estimation in our measurements. So here we have good results. I say good results because our previous models, previous tests gives to us a sigma and med metric around 0.056, and here where are most concentrated the data, we have something around that, and it is not our best model, but I will talk about this in a minute. So we have a comparison of older model version with the BPZ, that is the one of the most famous template fitting methods, and we had achieved better results than the BPZ for few objects here. These objects are not the same that these objects here, but I thought it is useful to show you how the machine learning, how this method can be powerful. And for the PDF matrix, sorry. Okay, for the PDF matrix, we have the pitch distribution. As I said, the shape of this distribution tells us how our model is under or overestimating the results. And this edge here, it tells us that our model is overestimating the results. So we can think, if we see the definition of pitch, we can think that this PDF here is most of the times at the right of the spectroscopic redshift. So our model is shifted all the PDF to the right of the value that we want. So the odds distribution, the ideal scenario, that is the odds distribution has peaks around close to 1, but there is not what was happening. But these results are not so bad, and also can be improved. And I will talk about that right now in the conclusions. So we do have the capacity. We are capable to predict redshift photometric probability density functions, but our model is not too good. It is overestimating our results, but it's possible to do better than this, turning our model, changing some parameters that defines the model, And we can do that also with machine learning. We use machine learning to improve the machine learning, and it's a work in progress. And also this model, these results that I showed here were my latest results and not the better results. Here we use this model that provides the better results we have to do the photometric relatives for entire Delve DR2 catalog, and it is available on this web page here. And so feel free to access this page. And there is a problem: if you access this page, you will not find the PDFs, because it's very, very hard to store the entire PDFs. But we are dealing with it. How many time I have? I mean, okay. So we are dealing with it. We developed a work framework to compact this PDF in a way that it can be feasible to start that. And I will thank you now, but I will just show you the results of our compacting PDFs. I have 1 minute. So we can reduce the problem that was occupied a 1.5 terabytes on disk for 200 million objects to 16 gigabytes on disk for 200 million objects, compacting these PDFs. And this is our metrics comparing the original metrics, photometric relative metrics, with the restored one from the compact vector. Okay, so thank you for the attention, and that was my first talk in English, and so thank you for the patience too. And yes, what's that?
All right, thank you, Gabriel. So questions for Gabriel?
Yeah, thanks for the nice talk. So what would you say that that you have learned with the prediction of all this PDFs with machine learning? So this is not a critic to, I mean, I do machine learning myself, but it's always the thing that after we do machine learning, it's also interesting to go back and try to think, okay, big picture, what have we learned in terms of traditional physics that we can actually understand? So even if you would have the function that the photo Z function that you said it was overestimating, if you would have, that picture that you would have that perfectly perfect prediction, then what? I mean, I'm just trying to sense what is the, I mean, it's great to have a method that works, but I'm wondering, and since it's not my area, so perhaps you can, elaborate.
So I don't know if I understand right, but you are asking what we have to do after our model are the best model possible.
Yeah, you find, let's say you have a deep learning model that fits it's well trained and fits your data and everything, and then you have so what then? I mean, what have you learned about that?
So we do that to provide photometric relatives for other researchers in the area that will use our photometric relatives to do the research that use photometric relatives, because we have, when we compare the amount of galaxies with spectroscopic redshifts with the amount of galaxies that do not have spectroscopic redshifts but have photometry, and we can estimate photometric redshift with this photometry. It's I don't know the word, but it's a difference very, very large. We have much more galaxies without a good redshift, that is spectroscopic redshift. We have so much gas without this redshift that that have these redshifts. So it's important to have a way to estimate and a consistent way to estimate that. So it also have their problems in machine learning techniques. So I could discuss this later about the range of the range in the parameters that this model works fine, and we have to be careful with that. But I think it's that. I don't know if I answered your question.
Yeah, thanks.
Okay, I think we have more time for one short.
No one else is asking. So I got confused about three different things in the talk. You mentioned about this sum of Gaussians, where you have, so at the end, your PDF is a sum of 10 Gaussians, right?
Yes.
That's the output.
10 Gaussians.
But also you use these legendary memory units.
Yes.
This is your machine learning thing to train, right? But the output is this 10 by 3 outputs for each.
Yes. Yeah. I can choose the model I want to use here if it's give to me this set of parameters.
Right.
What I have to minimize is a loss function that is made by combining these parameters and generating my PDF. And these parameters are actually my output. So this model here, I can build in the manner that I want, and we choose it, the LMU to do that, and including which is the LMU with attached to a dense layer.
Right. So you said that this LMU is like a recurrent network that normally is for like time domain things, but your input are just 4 numbers, right? G, R, I, Z.
We do not have time dependence here, but it's worked because we just tried to it's very efficient to time dependence problems, but not just to that. It's efficient to tabular data too, with no time correlation. But we can think in a way to give to the model the magnitudes and the colors in a way that it will recognize that as a time sequence too.
Right. But I mean, the difference here is that G, R, I, Z, the order matters, and in a way you're trying to see some correlation between them as if it was some kind of time correlation.
Yeah, probably the model see the inputs like that, but we one of the things we want to test is change the order of the G, R, Y, and Z to give the model. But I think it will not once the model starts with no information about magnitudes or about colors, I think it will not change the results.
Okay, that would be interesting to see, because if it doesn't change, then it's weird that this LMU gives anything additional to a standard neural network, right?
Yeah, in fact, the output of LMU itself is reasoned by a other type of network. So we do not have a physical meaning of the output of the LMU cell, because it's processed by other network here. Okay.
Well, let's thank Gabriel again. And now I think we have one last talk from Álvaro. I think it's Álvaro, right? Álvaro, you there?
Yes, I am.
Okay. You can try to share your screen, please.
Just a second. Then, can you see it?
Yeah, I can see perfectly.
Can you see my pointer as well?
Yeah, we can.
Oh, sure. Thank you.
Let you know when you have 5 minutes, okay?
Okay, thank you. So, first of all, I'd like to thank you for the opportunity to talk here. My name is Álvaro, and I am a PhD student from Universidade Federal do Rio Grande do Norte, and my advisor is Professor Farinaldo Queiroz. So today I'm going to talk about a proposal that we did last year, which is called Search for Dark Sector by repurposing the UVX Brazilian synchrotron. So just to summarize, this is a proposal to a new fixed target experiment that could be done here in Brazil to look for dark sector particles. This is a brief overview of the presentation, where first I'm going to talk a bit what is these dark sectors and specify a model that we use in the proposal, which is the dark photon model. And then I'm going to talk about the SETS proposal itself, talking about a bit of its properties, how it will work. And after that, I'm going to talk about the sensitivity of the experiment for this dark photon model. And I'm going to finalize with a summary of the properties of the experiment and some perspectives from future works. So first of all, what is a dark sector? Dark sector is a terminology used to talk about some kind of new models beyond the standard model that usually they have a dark matter candidate or particles that interact with dark matter. There's been quite a few talks already here in the event talking about dark matter, and there is a strong evidence that dark matter exists in our universe. However, up until now, we only know that dark matter interacts gravitationally. But we know that there is nothing against dark matter interact with the standard model particles beyond gravitationally. So we can assume that dark matter has some kind of other interactions with the standard model that are not gravitational. So there are many ways to do that, such as a Higgs portal or neutrino portal, and also the addition of another gauge symmetry, which will be an extension of the local gauge group of the standard model. So this dark sector kind of contains all of these possibilities to make these interactions between dark matter and the standard model. And in our case, and specifically, we consider the case of a dark photon. So in our case, the dark photon will work as a bridge between the standard model and the dark matter. And this is a very interesting model because the dark photon is one of the most simple extensions to the standard model, where you only extend the gauge group of the standard model by a U1 symmetry. So it's pretty simple. And it can be used besides the solving to connect dark matter with the standard model to solve other problems. So, and it's a very popular model because of that. So what is a dark photon? Dark photon, some people also call a hidden photon, is basically a new massive mediator that comes from these U1 gauge symmetries. And we know from quantum field theory that when you have this new U1 gauge symmetry, what basically happens is that you have a new gauge boson that mixes with the photon. And this mixing between the photon and this new gauge boson is given by this term here in the Lagrangian, where F mu is basically the strength tensor of the photon, and F prime mu is the strength tensor of this new dark photon. And however, this mixing is regulated by a new constant parameter here, which is called epsilon. And this epsilon parameter, since it regulates the mixing, it is also responsible to regulate how strong are the interaction between the dark photon and the standard model particles. Because since we have this mixing between both photon and the dark photon, this means that all of the charged fermions have a current with the dark photon as well. And this current is quite similar with the electromagnetic current, but it has the difference of having this epsilon parameter as well. So epsilon is a key parameter from this dark photon model, sorry. And usually you can calculate this epsilon. And for example, I put here a Feynman diagram, which will be how could you calculate this guy in one loop, for example, where the fermions inside the loop are the fermions that interact with the dark photon. However, usually we consider it to be a free parameter that we can use to fit our data. And that's the approach that we will take here. And another interesting fact is that the mass of the dark photon, it can, of course, you can always put a new scalar, the scalar develop back an expectation value, we break the symmetry, and then you have a value for this mass. but we also consider it to be a free parameter. So the main parameters for the dark photon model are the epsilon and the mass of the dark photon. And as I said, since it has this dark electromagnetic current, which is basically the Fermis interacting with the dark photon, you can search for them in many different experiments. For example, here in this figure, that's kind of a summary of current and projected bounds on these properties, where we have here bound on epsilon squared as a function of the mass of this dark photon. As you can see, we have quite a lot of experiments here. And we have some beam dump experiments with E774, with E141, and Orsay E137. And we also have colliders such as BABA, LHCb, and we also have some low energy experiments such as PADME, VEB, and MAPS. In our proposal, we will go in this low energy experiment. So our main competitors are these three experiments here. So up to now, I've only talked about some general properties of a new dark sector or the dark photon model. So now I'm gonna focus a little bit on the proposal itself, which is here's the archive number, if any of you guys are interested. So the name of the experiment is Search for Dark Sector, as it is in the title. And we propose this new fixed target experiment, which basically means that you have a beam of particles, which is directed at a target. And then you see what happens. That's the main idea here. And our main plan is to use this setup to search for dark sector particles. And in our proposal, we consider the case of the dark photon. And the idea of this experiment is that we initially, in fact, just a little story, initially we thought of proposing this experiment to be done at Sirius. However, we soon found out from the people of the LNLS that could not be done, because otherwise we would have to change the whole experiment. And this cannot be done since thousands of people use the Sirius every year. So then they talked to us, well, you cannot use Sirius. However, there is UVX, which is Sirius' predecessor and was shut down in 2019, that has some of its subsystems that are not being used. So we can take these subsystems from UVX and apply to this new experiment. And that's the main reason why in the title of the presentation is Search for Dark Sector by repurposing the UVX Brazilian secret, because we will take those subsystems and then make them, use them to this new experiment. And yes, in this new experiment. So how can we produce a dark photon in this experiment? As I said, it's a fixed target experiment. And in fact, our beam is a beam of positrons. So we have this beam of positrons, which will hit a target, which we consider to be a diamond target. And then we have a few ways to produce dark photon. The first one is the simplest, which is electropositron annihilation and produce a dark photon. However, since we are considering a light dark photon, there is the possibility that we will not even see the dark photon. So this channel is not very interesting for us. But consider, so we need to have some channel where this dark photon is produced with another particle that can be visible experimentally. And then we have those two cases here. The first one is called electropositron annihilation, where these guys annihilate into a dark photon and a photon. So even if we do not see the dark photon, we will see the photon here. So this means that we can calculate or measure the properties of this photon that was produced and use it to produce some bounds in the properties of the dark photon. And the second case is the dark photon brainstorm, where the dark photon will be emitted by a scattering into the target. However, in this case, the visible particle will be the positron as well, with the positron, and we can measure the properties of this positron to put a bound on the dark photon properties. So now let's talk about the experimental design. Since we are trying to look for dark sector particles, we need to have an experiment that is able to first of all, produce these particles, and then to measure these standard model particles that are produced along with these new dark sectors in a precise way. So let's take a step back and try to understand what would happen here. So first we have a beam source. This beam source will be directed at a target. And as we know from quantum field theory, this will produce many particles. And also there is a possibility that part of this beam will just pass through the target, will not interact at all. So first of all, we need to measure these properties. The usual way is by adding a calorimeter. So we add a calorimeter here, which is our case an electromagnetic calorimeter here. However, since there is part of the beam that we just passed through, this part of the beam will hit the calorimeter. And this will make the calorimeter have a lot of events that we do not want because it just passed through. So what can we do? We have simplified. We have two options actually. The first one is to make a calorimeter which has a hole. Then this beam will just pass through the hole. But in the same way, at the same time, if you do this, we'll lose some of the events. Or you can deflect this beam. And in that, that was the choice that we made. That we'll deflect the beam, so we will have a whole calorimeter. And to deflect this beam, we need a dipole magnet. And this will deflect the beam. And at the same time, by adding the dipole magnet, we can also deflect all charged particles that are produced. So this is a very interesting case because it will reduce a lot of the events in the calorimeter. However, it comes with a price. The price is that we no longer are able to measure the second case of the brainstorm, because if a positron is just scattered, it would be deflected as well. So we only have to choose the first case here, which is the electron-positron annihilation. And considering that we are able to measure quite well the energy of this photon, we can use this missing mass technique, which is basically for momentum conservation, to infer some properties on the mass of this dark photon. And so this is a very interesting case because we can use, with just measuring the photon energy, we're able to produce bounds on the mass of this dark photon because we know the properties of the beam, and an electron inside the target is approximately at rest. So we are able to do this measurement and find a bound on the mass of the dark photon. However, we want to know with the other parameter of interest is epsilon. So we need to use this bound on the mass of the dark photon on the cross section of this process, and then we put a bound on the epsilon as well. And so, as I said, this is the cross section of this process. And as you can see, this cross-section is not that long, but it has a few divergences, especially in S equals 0 and S equal to MA squared. So what this means? This means that the range of parameter space that we are able to bound with this experiment are limited by the center of mass energy, which makes sense. We cannot produce particles that are heavier than the center of mass energy. And this is a very interesting result because this means that we have a bound. Even before we measure anything, we know that we have a bound on the mass of the dark photon. We can only look up to this value here. And so to make a to show you guys how this works, I made a plot where we have different values of here. In fact, is the energy, the beam energy. However, since the electron spirit light is basically the same of S. And then we find that indeed, as we make the energy larger, we are able to reach Fourier regions in the dark photon mass. So this is this shows that everything is okay, it's working fine. However, as I said, since we have this dipole there, this means that all neutral particles will hit the calorimeter. And this is a problem because this means that we have a backbone that basically we cannot get rid of unless we made some changes in the analysis. And the standard model by itself is able to produce a lot of background events. In our proposal, we consider a few cases of these background events because we are assuming initially UVX is able to produce a bin of 1.3 GeV. But we consider another case where we are able to make an upgrade to this energy to up to 3 GeV. So we calculated here this background, which are basically the process from the standard model that produce photons. So those photons will be detected by our calorimeter. And then we have this table here, where we have the contribution from electropositive annihilation to 2 photons, the photon brainstorming, and also the electropositive annihilation to 3 photons, and this 4th process here, which is basically you produce a photon in the final state. And as you can see, the contribution are quite different in both configurations of energy, but at the same time, the size of this cross-section is quite big. But our main enemy here, if I might put it like that, is the brainstorming, because it has the highest contribution. However, thankfully, actually, we found out that this contribution all of them actually can be reduced from cuts in our analysis, be cuts on the energy of the photon that we are measuring, or cuts on the angular analysis of the angle of these photons where they hit the calorimeter. So we are able, in fact, to reduce the number of events in the calorimeter. Sorry?
That's okay.
Oh, okay. Thank you. So now, since we discussed the background, we consider optimistic case where we are able to reduce the background as much as we can. So in this, as I'm saying again, this is a very optimistic case because there is nothing we are not sure if we are able to, in fact, to reduce the background to 0 without building the experiment. But however, we consider this optimistic case to calculate a projection of the sensitivity of the experiment. And here we have those 2 plots where the plot on the left is a plot, both plots actually are a plot of the epsilon squared as a function of the mass. And the plot on the left is a configuration of 1 GeV beam of positrons, and the target is of 100 micrometers. So it's a quite thin target. And the plot on the right is a plot of a 3 GeV beam of positrons, and that has a bit target which is a bit thicker, which is 500 micrometers. And in this plot, we have some contributions from older experiments, such as the beam dumps experiments here, which are E774, E141, or say in E137. And we also have some data from colliders, for example, where unfortunately I wasn't able to put all the names here because otherwise it would become a mess. But we have the contribution from LHCb, Babar, Bell, and also NA48 as well. And then we also have some data from our competitors, which are PADME here, which is this dashed black line here, VAP3, which is also a dashed black line, and the MAPS, which is this other black line here. And the sensitivity from sets is represented by these green regions here. And in our analysis, we consider 2 different configurations for each case. The first configuration here is for the case where we have a 820 PB-1 of luminosity, which is basically the same of consider the case of configuration with 10 to 10 positrons on target per second by 90 days. And the second case is by 1 year. So the same configuration, but running for 1 year. And as you can see, we are able to probe quite a large region of parameter space. Especially, we're able to probe this region here, which hasn't been probed yet. So this means that this experiment is able to produce some bounds that were never seen, that were never covered yet, this region of parameter space. So this means that SADS has a really nice prospect to being able to find something. And it is also a very competitive experiment as well, if built. And here for the case of 3GeV, the curves go a bit further in the mass of the dark photon, which is expected from the cross-section, and we can cover even more region of this uncovered parameter space. So this means that if this experiment is built, it will be a very competitive experiment. And also, as an addendum, it will be the first experiment of its kind in Latin America. So this will put Brazil in kind of in a leadership position to look for this kind of particles. And as I said, that first was a very optimistic case. And so we wanted to do a more realistic analysis. So we consider a case with the same configurations. However, the number of background events is similar to the number of the signal events. And then we found out that, just to compare here, the curves go a bit up, so we lose a bit of sensitivity, but we're still able to cover this uncovered region of parameter space. So this shows that SADS is indeed a nice, a good option to look for dark sector particles if it's built. So to finalize my presentation, I'll present some summary and perspectives. First of all, I would like to say that SADS, as I was saying before, SADS has a pretty nice potential to look for dark sector particles, in the sense that if SADS is constructed, it will be able to look not only for dark photons, because we are using the missing mass technique, so it doesn't matter which particle is produced along with the photon. It can be a dark photon, it can be a light scalar, it can be a pseudo-scalar particle, it can also be an axion-like particle, which is, those two cases are the ones that we are working right now. And another very interesting case is that, just going back here, some of these limits here are based on visible searches. But since SADS is using missing mass techniques, we can also, our limits are also valid for invisible searches. So we have an experiment which can work in those two forms, which is pretty nice. And also there's, and this, even though, and as I said, since you can look for these two regions of visible and invisible searches, they also have the versatility to look for many other dark sector candidates, and it will be the first experiment in Latin America. So we are currently working on these other possible particles that we can search for in SADS, and I hope it is in the internet in a few months. So stay tuned for the latest results in for this very nice proposal. And that's all. I would like to thank you for your time.
Thank you, Álvaro. If you have any question in the Zoom, please unmute and ask, because we can see the screen right now. So any questions for Álvaro? Yeah.
Yeah, thanks a lot for this. This was very interesting. So I guess the big question for your experiment is, what is really the relation between your signal and background? So you show that
yes.
You could you showed this zero background case and this other, but do you actually have a selection? And because your chances of getting funded in the end, it's really because, I mean, what is this a real projection, and what kind of, if you have a selection, what kind of cuts do you have? I mean, is this something, because you have to demonstrate that this is feasible in this respect? So
yes, so regarding the cuts, in fact, that's a bit tricky, because even though we can make some simulations to kind of make kind of look, well, this cut works better than this. We are only able to make some real cuts when we have some prototype of the experiment. But as I was saying, we consider actually another case where is the case where the background is a bit larger than the signal, which here the 10 times of the signal,
right?
Which is present in this plot here. And the sensitivity goes up as expected. We will lose sensitivity since they have higher background. But still we're able to still probe this region. But as I said, that's a problem as well, because we don't know how many of the background we will see. Only when having a real prototype we'll be able to measure that.
In simulate, you don't necessarily, I mean, before building a prototype, you need to have some whole simulations, like detector simulations are very complete. And then you see whether or not it makes sense or not. Because you say 10 signal, but it could be whatever if you don't and then nobody's going to be convinced before you can actually make a projection of what this relation is.
Yes, because the maximum that we can, the background can be simulated if you use some GN4, for example. We can use it to simulate. The signal is a bit trickier because since it is a new interaction, it's a bit more troublesome to make the simulation. But we can do actually a GN4 simulation, and that's something that we want to do. But in the future work, we are thinking of doing that.
Okay, thanks.
Okay, we are out of time, so let's thank Álvaro again. Okay, so now we have the break and we come back in 30 minutes, right?
Oi, Martin, tudo bem?
Okay. Okay, let's start the next two presentations. And the next presentation is Farinaldo Queiroz.
All right, so can you hear me? Yes?
Yeah.
All right. So hold on, let me share my screen. All right, so good afternoon, everyone. So thank you so much for coming back in and waiting for this talk, 30 more minutes roughly. So I won't take long. So I'll be covering different aspects of dark matter. So I look at the program and I believe that'll be complementary to previous talks, discussing some aspects of dark matter. So first, I'd like to really thank all my students who are deeply involved in many of the results that I'm gonna present today. So there are two takeaway messages that I'd like to get across to all of you in the room, is that dark matter, as you've seen so far, is an interdisciplinary program, and is the presence of dark matter is present at different scales and epochs of the universe history. So to me, dark matter is quite compelling. And I guess I don't need to convey that message anymore. And I'm just like to quote James Peeble in his Nobel Prize ceremony, where he states that he's deeply impressed with the way dark matter has explained all cosmological observations so far. And I would say that I agree with him. So before I really go into the details of the results, I'm just going to reveal some of the aspects of dark matter searches, because as you've seen in the very first slide, my talk is the fourfold search for dark matter. So there are supposed to be 4 ways. So I'm going to cover these 4 ways during the talk. So to me, it seems to be more than 4, but okay. So the first one is direct detection, and it refers to measuring nuclear recoils of dark matter particles that interact with atoms located at underground laboratories. And this interaction produce some light if you have a silicon scintillator detector, such as xenon and other scintillator materials that we have out there. And what you see at the end of the day is some light, and how this light is produced, you can discriminate signal from background. That's roughly what direct detection is. You can also have other techniques, readout techniques, to somehow constrain the properties of the dark matter particles. That's one of them, through scintillators. And the physical quantity that we are interested in is the scattering rate. This DRDE is just stating the number of scattering events we have seen in a given detector, which does depends on the velocity distribution of the dark matter particle, which is called FV. And you have to integrate over all space. That's why you have this D3V. V stands for the velocity, incoming velocity of the dark matter particle. As the detector is at rest, therefore V is just simply the velocity of the dark matter particle, which we do know from astronomical observations such as Gaia and etc. We have also the scattering cross section of the dark matter particle is scattering off nucleus of this d sigma dE, which at the end of the day can be translated into the dark matter scattering off quarks through some calculation procedure. And this F stands for the form factor of this scattering. And these rho chi and m chi are the dark matter density locally, and m chi is just the mass of dark matter particle, and m is the mass of the target. So what I want to stress is that the scattering cross section, or the signal observed at direct detection experiments, does depends mostly on the particle physics side, is on the scattering cross section in the dark matter mass. Therefore, these astrophysics aspects, but I will not focus on, and there's also some nuclear aspect, but I want to really stress the difference between them. So the particle physics side, which is the one that will be focused on during this talk, which is scattering cross section and the dark matter mass. So this picture is quite popular in all conferences. I think I've never attended a conference in dark matter where I did not see this plot. Seriously, I've never seen a conference in dark matter where this plot or something very similar to it does not pop up. So this is just a race of direct detection experiments trying to search for those dark matter nucleus scatterings happening at low energies, and all these solid curves represent current bounds, and these dashed curves represent projected limits from a variety of detectors. But you can really see there's a race for observing a signal of dark matter, or which at the end of the day, since we haven't seen any positive signal of dark matter scattering, therefore those observations, they result into limits. Anyway, and we have also this indirect detection. To me is really, really interesting, because I do like to see the sky at night. And indirect detection, basically that's what it is. So instead of just picking up your telescope at home, you have a 30 meters wide telescope, So that's basically the difference. And this signal that you observe, I think Ulysses has covered this before, or I believe Ulysses will talk. Ulysses, I think we'll talk tomorrow, right? Can you confirm that? So the signal from the sky, you have a flux of dark matter, and this flux of dark matter particles, what you have at the end of the day is two dark matter particles coming in, and they interact with each other and annihilate and produce gamma rays or cosmic rays. And as you have two incoming dark matter particles, the signal you observe depends on the number density squared of the dark matter particle, which is represented by n chi. Obviously, also depends on the annihilation cross-section of those dark matter particles. And dNd is just saying how many or how many gamma rays are produced per annihilation. And this d omega is just a solid angle, the portion of the sky that you are observing. And there are several detectors that can search for signals from the sky originated from dark matter annihilations, such as a form of neutrinos, in a form of gamma rays or cosmic rays, antimatter, etc. And the key thing is, as far as particle physics is concerned, is that the key quantity for us is, as a particle physicist, is the annihilation cross-section and the NDE, which is the energy spectrum, which does depend on the final state that you're considering. So as you've seen previously, we have the scattering cross-section of dark matter, that's one, and the dark matter mass. In this case, you have the annihilation cross-section instead and the energy spectrum. There is also some dark matter mass dependence here built in this number density. But anyway, the dark matter particles set aside, the one you have the annihilation cross-section and the other one you have the scattering cross-section.
One in the Atacama Desert.
And this one, let me stop the video for a second.
One in the Atacama Desert.
Which I really love it. So I think Ulysses, you should, if you're in the audience, you should broadcast this video to everyone who's vaguely thinking whether astronomy is nice or not. Because to me, this video is quite amazing. So what this video is going to show you is that how a telescope can observe gamma rays at the ground instead of being in the sky like satellites. But instead of, before showing you the video, what you have at the end of the day is you have telescopes measuring photons, and as they measure photons, if the amount of photons you observe is consistent with the amount of photons you expected from astrophysical sources, you can, if it is, you can place an upper bound on the amount of photons you observe in a given area of the sky. This is translated as an upper bound on the energy flux of the photons observed from a given region of the sky, which is this d phi dE. So let me just run it for a moment because I really love this video.
Another atop the Spanish island of La Palma. The Cherenkov light will flash and disappear. This faint glimmer can be collected by the telescope's mirrors and reflected into cameras, capturing 1 billion frames per second. The light will be captured by sensors able to detect a single photon and turn it into digital data. Data centers will store and process the information.
Well, the video is 3 minutes long, so I cut it short. But I guess you can grasp the idea. So it's quite exciting. And so what I just want to emphasize that direct detection is sensitive to scattering cross-section, and indirect detection is sensitive to the annihilation cross-section, which, depending on the particle physics model you have, they're completely unrelated observables. So to me, this is quite impressive that CTA will surpass the previous telescopes by roughly an order of magnitude, depending on the dark matter mass you're thinking of. So for instance, you have the dark matter mass in the x-axis and the annihilation cross-section, the y-axis. And the CTA projected limit would be this solid black line. And you can see, for instance, for Haas, is basically almost an order of magnitude, depending on the dark matter mass you're considering. So CTA will really come and give us a different perspective of the gamma ray sky. So to me, this is quite interesting, especially because CTA will cover the region below this line right here. This horizontal line represents the naive expected annihilation cross-section for dark matter particles, which reproduce at the end of the day that 27% of the energy budget of the universe that we have seen with this CMB data. So if you have some dark matter particle to represent 27% of the dark matter density of the universe, naively speaking, you expect the annihilation cross-section to be around that horizontal line. And CTA will cover, you'll go below the horizontal line. So therefore, in that region of prime space between these 2 points here, this crossing point and this crossing point, CTA will cover all multitude of models which have these dark matter particles giving rise to the right relative density of dark matter and at the same time, at once. So it's quite exciting, sort of model independent probe of dark matter. So, and this one's a collider accelerator. Nicely, Alvaro's talk came before mine, so I will not dwell on the details of these search for light dark sectors at the sets. I just like to emphasize, so now I've seen his talk, I'd like to just stress 2 points that perhaps were not covered during his talk. Is that first one, this we have ongoing and data taking accelerator going on right now, right, in Campinas, in São Paulo. The idea for this detector UVX is not to take place right now in parallel to the LINAC we have today, because that's not feasible. So we have talked to the director of Sirius to see if that would be possible. He said, yes, they do have some components of the predecessor of Sirius, but they cannot run them together independently. They cannot do that. The only thing they can do is, eventually, Sirius will have to stop for some maintenance. And when that stops, then they can then replace the electron beam they currently are using with a 2 GeV electron beam, replace it with a positron. And if that happens, that we could really make that happen if it will happen at the end of the day. So only then will we be able to have indeed a dark sector detector in Latin America if we are convincing enough that we have a strong case for building a detector like this. And addressing the question that was raised during Alvaro's talk concerning this plot right here. So we're questioning whether it's feasible or not having this background free or background number of signal or 10 times the number of signal. So how do we know this number? Because we have not carried out a full Monte Carlo simulation, including detector effects. We have not done that. And so that's one of the advantages that we have this guy right here, Vendelin. So he's a detector guy who is also one of the guys who built a detector just like this one at Padmi in Frascati, Italy. And he's one of our detector wizards in this project. And these numbers that we came up with to him are very, very conservative. So I'm saying I've never done full Monte Carlo simulation using GEONT in my life. But according to the guy who has done it many times in his life, we are being very, very conservative concerning our estimates or our projected sensitivities for dark sector searches. But those numbers were picked at random, so just to see how the curve shifts as we increase the number of background events. But according to him, are very conservative. And I was just looking before my talk, the PADMI collaboration has put out a paper where the number of background events is very similar to the number of signal events. So this number should be, the ratio should be around 1 for PADMI, and PADMI has a very similar setup as the one we have. So naively, we expect to have very similar background situation. Okay. Anyways, but just to emphasize once more that the idea here is that, okay, we have an accelerator that could be potentially built in Latin America, in Brazil, and would be the very first of its kind in Latin America, the very first really Latin American dark sector search. We do have dark sector experiments such as CTA that will be built in Latin America, but they are not Latin American detectors. They are from Europe and eventually brings it to a site in Latin America. It's not really Latin American detector. This one will be one, okay? So it will be really Latin American having a leadership role as far as dark matter searches are concerned. To me, this is groundbreaking, if that happens. Anyway, so now I really go to the key point of my talk, which is, to me, I separate as old life and new life. As a PhD student, I do remember that people were saying, wow, there is a new era in dark matter. And the new era in dark matter when I was a PhD student was that we do not really just focus on direct detection of dark matter or collided searches for dark matter or indirect detection searches for dark matter. We should actually, I would hear my supervisors at Fermilab saying, look, for now, the new era now is that you have to combine the three. So you cannot just use one data set. If you have a given particle physics model on the theoretical side, not experimental side, on the theoretical side, if you have a model, particle physics model, you have to really account for all the three ways how you can probe dark matter. And to me, to my students, then I say something different. I say, look, now we are in a new era, but the new era is not this direct detection collider and direct detection way. You have now more ways how you can probe for dark matter, thankfully for the progress that we've made in the past decade concerning astronomy and cosmology. And those stands for neutron stars, black holes, and cosmology. And I'm gonna discuss them now. So neutron stars. So first, let me give you the vague idea of what's going on. So what happened is you have a neutron star, you have one, okay? But I will do for a population of neutron stars. But you have one neutron stars. If let's say that you know somehow the temperature of that neutron star, or you track the evolution temperature of the neutron star for a while. From that, I don't care what the equation of state is. I just measure the temperature of this neutron star. If the neutron star, given the neutron star evolution, if the neutron star features a temperature evolution which does not follow what a neutron star, regular neutron star should do, the evolution of the temperature, which should be decreasing with temperature, with the age of the neutron star. If it's not decreasing, it's rising or flattening out as the time goes on, then something weird is going on at the neutron star. And that something weird might be a process that's heating up the neutron star as the time goes on. But okay, I'm not going to look at one neutron star. At the end of the day, I'm going to look at a population of neutron stars because I don't want to look for dark matter at one object, which if it is dark matter causing the heat of the neutron star, because I will not convince anyone in the whole world in their right mind that dark matter is causing the heat of one neutron star and everything else. All neutron stars are just as the same. They are not changing at all. But one neutron star in particular is changed by dark matter. No one in the right mind will believe that. Therefore, I have to look for a population of neutron stars which present some weird temperature. And that's the proposal that is being presented right now. And that increase in temperature could be resulted from the annihilation of dark matter particles, the scattering of neutrons present in neutron stars. Can be scattering of electrons, because neutron stars do also have electrons. in a smaller amount, but do also have electrons, could be also scattering off protons in a smaller amount, but could also scatter off protons. And the idea is to probe the scattering cross section of the dark matter scattering off whatever. So that's the whole idea. So if you do that, you do some calculation. I'm not going to go through the details of these calculations, but at the end of the day, this scattering cross section sigma is somehow affects the temperature of the neutron star throughout the history of the neutron star. It affects this. You can compute how much it would affect and how much the temperature of the neutron star would increase. To me, it doesn't really matter what the temperature of the neutron star is. To me, what it matters is the increase in the temperature. Well, to me, the increase in the temperature that a dark matter particle can do in a neutron star is about 1,700 kelvins. That's not much. For those who are not familiar with neutron star physics, such as me, 2 years back, such as myself, 1,000 Kelvin in a neutron star is not much, okay? It's not much. So in order to see an increase in 2,000 kelvins in a neutron star, you have to look for very, very old neutron stars where their temperature are very, very close to zero. And then at 2,000 it makes a big deal. But if the temperature of the neutron star is like 10,000 kelvins, and then do an increase of 2,000 is not much. It's like within the error bars, of the measurement. So you cannot do much. But if you really track really old neutron stars, you can perhaps probe those neutron stars. And then comes to a different, before really going to the details of these measurements, let me just emphasize one thing. Someone might ask, I even ask myself, look, I'm not an astronomer, I'm a particle physicist who do like to work with the cosmos, let's say. So I've asked some astronomers, I said, look, can I really measure pick up neutron stars which have temperatures around, let's say, 1,000 kelvins or so? Can I really measure them? And they've told me, for now, with the instruments we have so far, that was like 2 years back, we do not see them. It's just impossible. We cannot catch them. However, there is some telescope that will come up, like in 2 years from now, called James Webb Telescope, that might have the ability to capture those neutron stars. I said, okay, awesome. So I'm gonna now really write a paper saying that perhaps in 2 years, we're gonna be able to observe this increase in the temperature of neutron star with a projected telescope called James Webb. However, during the process of James Webb, some of the funding that would be used to construct a camera capable of observing radiation equivalent to this temperature of neutron stars of 1,000 kelvins or 2,000 Kelvin did not go through. So James Webb, as it is today, it definitely cannot observe an increasing in temperature of neutron stars of around 2,000 Kelvin. It cannot. However, there is a community involved behind, and we are pushing for this construction because this camera was previously in the proposal, but at the end of the day, it did not go through for some budget arguments. And now you're saying, look, this camera is really important for the purpose of using neutron stars as dark matter labs. And just to convince you of the importance of neutron stars or this camera to be installed at James Webb, look at this. So this is, I just picked up a model, okay? You don't have to believe in the model. I just picked a model. I can pick several models. So this model is like this. I have some fermion chi, which interacts with some quarks, Q, through some scalar. This scalar is phi. And this scalar is a pseudo-scalar particle. What you can see is the following. So everything above this curve, these dashed curves, are excluded by direct detection experiments along those dashed lines. Remember, you should emphasize, Darwin is not an existing dark matter detector, it's a projection, which will be this dotted curve right there that goes here and rises up. So that's the projected curve for Darwin. And this the very last dotted line is the neutrino floor, is the way where supposedly we cannot go beyond. We cannot probe with the ongoing techniques in direct detection experiments. We cannot go beyond these dotted line. And these curves, these colorful curves here, are showing the parameter space where neutron stars can probe. So everything from on that red curve can be excluded by neutron stars. Everything on top of this pink or purple-ish curve can be excluded by neutron stars. What I'm saying is, so let's say I have a dark matter particle of let's say here is 10 TeV, or 100 GeV, or 1 GeV. Everything here I can exclude with neutron stars, and they will never be excluded by direct detection experiments the way they are presented today. They will never go that far. But neutron stars present an opportunity to probe for dark sectors which have masses which are, let's say, from 10 to minus 2 JeV to 10 to 8 GeV, and cross sections which are really small and not accessible by direct detection experiments. And then let me pick a different model. Oh, okay, maybe you pick this model just to show off. No, I'm not showing off. So let me pick a different model, such as scalar dark matter and scalar mediator. Now, instead of showing cross section, I'm going to show masses of particles which are easier to grasp, to understand. So this MA is the mass of my mediator, my vector, my scalar mediator. And MK is the mass of my dark matter particle. Now it's just masses, okay? So what I'm showing here is that everything above the curves, are okay by a given detector. So let's pick this, for instance, this blue dashed line right here that I'm going over it. Everything above this curve, above is okay. Everything below is excluded. Everything below is excluded. So as you can see, the xenon one-ton data, which came out, I think was in March last year, so roughly a year ago. So everything below this curve is excluded, below. And neutron stars is, as you can see here, this region here below 10 GeV, this xenon detector is not sensitive to it. However, neutron stars are. They lose by a lot to direct detection experiments for dark matter masses above 10 GeV, but below 10 GeV, they are the only way, because neutron stars probe the scattering cross section in a different way. So I will emphasize something that's really important that I have forgotten. So let me show just a different case where the difference is striking. Now I have a different model, scalar dark matter in vector mediator. This one is scalar dark matter and scalar mediator, and now this is scalar dark matter in vector mediator. The same way, mass of the mediator in the y-axis and mass of the dark matter in the x-axis. As you can see, direct detection experiments will exclude everything below the curves, below. Look where neutron stars are, like 1, 2 orders of magnitude stronger than even the ultimate direct detection experiments will not even dare to compete with neutron stars by 2 orders of magnitude. And scalar dark matter in vector mediator is a popular model. I'm just picking models, okay? This is just to show that neutron stars can be truly made dark matter labs. And let me emphasize why. I haven't discussed this so far. So why neutron stars are so special? They are so special because they are compact, as any other compact object. The point is that neutron stars we can probe well. So neutron stars are so compact, well, so dozens of kilometers in radius. So they're so compact and massive that when dark matter particles are in the vicinity of the neutron star, they are attracted by their gravitational potential. Well, they're attracted so fast that the velocity of those dark matter particles are large. Look, the velocity of dark matter particles are large. It means is the momentum of this scattering process is very, very large. However, the momentum exchange in these direct detection experiments, the usual ways are small. So you are probing the scattering cross-section at different momenta. That means is that you are probing dark matter particle processes at different momenta or different velocities. And why is this relevant at all? Well, this is relevant because in particle physics, when you learn particle physics at undergrad or in more advanced classes, you learn that the scattering cross-section, many of these scattering cross-sections we know, even in this standard model particle physics, they do depend on the momentum. Therefore, if you have a cross-section which increases with the momentum, I need to use neutron stars, not direct detection experiments. If they do not depend on the momentum, then direct detection experiments usually will take the lead. But if they do depend on the momentum, neutron stars are very good because the momentum is small for direct detection experiments. If the cross-section depends on something small, the cross-section is small. But for neutron stars, it's the other way around, increases with the momentum. Therefore, neutron stars are very good and complementary and orthogonal to usual direct detection searches. How much time do I have? How much time I have? 5 minutes? So?
More 5 minutes.
Okay, all right. So now I'm going to discuss how dark matter could be probed with cosmology. This is something really recent. I mean, I have to say I'm not an expert in cosmology. Most of the things I learned with Martín when he was lecturing cosmology in Andrés Vieca School quite some time ago. And so, however, it's quite interesting. So just to remind you that we have observed that we have a collective evidence that the universe is expanding too fast. So it's called the Hubble problem or the Hubble constant problem, the Hubble rate problem, whatever you want to call it. It's not to me as a particle physicist, well, it's not really a problem, but however, there is some discrepancy between the Hubble constant, which measures how much the universe is expanding, the measurement of the Hubble constant using local measurements, and the measurement of the Hubble constant, which is inferred, not really a measurement, from CMB data. CMB data, you just do some statistical analysis of the CMB data, and you can extract from CMB data what the Hubble constant should be. And then you compare that value with the Hubble constant that you measure today, just looking how Cepheids are moving away from you. And those two quantities do not match. CMB prefers the Hubble constant to be around 67 kilometers per second per megaparsec, whereas local measurements is around 73, 77. There is some large errors in the right one value, okay? It can be 70, 71 or so. But anyway, there is some discrepancy, and we were thinking, well, could somehow, if there is really a discrepancy, could this discrepancy be at all connected to dark matter, to some dark sectors? And it actually can. So if you have this chi prime is some dark sector particle, which is heavy, and chi is some dark matter particle, if they interact with each other, if one decays in the other, so dark matter is produced through the decay of some heavy particle, producing a photon, a neutrino, a Higgs, you name it, whatever, it doesn't really matter. What really does matter is that this chi, dark matter, is produced through the decay of some of the particle. That's all we care about. If that happens, if this chi is really heavy and dark matter is produced through the decay of other particle, this chi, dark matter, is boosted. So it behaves like radiation for some period of time. And when dark matter is behaving like radiation for some period of time, it behaves like radiation. And what is radiation? Radiation is like neutrinos. So dark matter, if it's produced through the decay of some heavy particle, it mimics the effect of some neutrinos. And what neutrinos do? Well, when you do redo the analysis of the CMB data analysis, when you redo it, so you have one collaboration with, I know, for 400 people. So you redo their analysis, take into account the fact that dark matter is not simply non-relativistic. Actually, it comes from also some amount comes from the decay of some heavy particle. If you redo Planck analysis, if you redo that, you find that the H naught that Planck collaboration reported was not supposed to be 67, was supposed to be 70, 71, 72, depending on how you analyze the data. If you include just the lambda CDM and then include that non-thermal production or the decaying production of dark matter, the Hubble constant, for using Planck data, basically, you can get different values. So depending on precisely the data set you use, you can have these bands here. So for instance, you can reach H naught, the Hubble constant, around nearly 70 or 69. You're increasing. Remember, it was 67 where it was right here before. And now it can reach around 70. And depends on the mass of the particles involved. And also, if you also invoke, and then you do really introduce some cosmology into the picture, like say, we have some dark energy component, which is a phantom-like. The equation state is not just like dark energy. And then you can have larger values of H naught. So H naught now can reach 674, 73 or so. So what I'm just trying to say at the end of the day is, I'm a particle physicist. I build model for in my daily life. It's very, very common to have a particle physics model where dark matter is produced through the decay of some other particle. I mean, this is really common. But I've never noticed, that never crossed my mind. I said, okay, I don't care. Dark matter is produced through some other ways. I don't care about this decay. However, I realized that this decaying mechanism actually might be able to solve a cosmological problem. So my particle physics stays the same. I now just look at this decaying process that already existed in my model, but I overlooked in the past. But now I say, look, this decay that I overlooked in the past actually might be able to solve a cosmological problem. And we did some analysis for many different models, but I'll not discuss this in more detail. I just like to thank all of you for your attention. And that's the picture of my current group. And I'd like to thank you, all of you, again, for staying with me all this time. Thanks.
Thank you, Farinaldo. Any questions?
Thank you for the talk. I was interested in this last part about cosmology because I recently saw a work you and Álvaro and Nelson.
That's the one. This one. Hold on. This one.
Yes, yeah. This is Jesus Internet. Would you elaborate? I know that you're focusing on the phenomenology and the detection, etc. Could you elaborate a little on the model on this work?
Yeah, sure. Okay. So the idea, let me recap a bit. So what you have is the only thing, the thing that we care most is the non-thermal. It's called non-thermal because these chi and chi prime do not have to have the same temperature as the particles in the standard model. So they do not have the same temperature. They are detached. It's called non-thermal. Anyways, so you have chi prime decays into chi. This dark matter is produced. It can be produced relativistically, right? If the mass ratio between these two particles are large. So if chi prime is very heavy, you produce chi with a very large kinetic energy. So chi can be, if the kinetic energy of chi, which is dark matter, the kinetic energy of chi is much larger than the mass of chi, chi behaves like radiation, like neutrinos, like electrons. Electrons at some point were relativistic in the past, right? When they're
Se você estiver ouvindo, você está congelado, Farinão. Alguém está aí? Alguém? Álvaro está aí? Maiara?
Yes, his internet is not working.
Okay.
He asked me to.
Ramon? Ramon, tá ouvindo? Ramon? Ramon?
Hello, everyone. Sorry, my internet. Hello, can you hear me?
Hello.
Okay, I'm using my mobile data. So the internet at the institute just went off. So I'm just, so can I continue answering the question? Unfortunately, I cannot show my slides.
Use the next.
Okay.
Yeah.
So let me just address the previous questions. The previous question. So what you have at the end of the day, so you have a dark matter part which is produced through this decay of this heavy particle. And then when you redo the CMB data analysis to see what would be the Hubble constant extracted from the CMB data analysis, introducing this decay, which Planck collaboration does not include, then the Hubble constant increases. However, it does not increase to the point of reaching Hubble constant around 72, 73, in agreement with local measurements. Therefore, if the Hubble constant, it is indeed 72, 73 kilometers per second per megapascal, if it is indeed this value, the lambda CDM model does not suffice. Does not suffice. We do need some to go beyond the lambda CDM model, even including the decay process. And then that's why we include this femto-like cosmology, which is simply taking omega, the parameter which relates the equation of state of rho and the pressure, the density and the pressure, to be different than -1. But if you do include that, and then when you redo the CMB data analysis, and then you can increase the Hubble constant up to 72, 73 or so. So that's all. Did I answer your question?
Yeah, but just the omega you're talking about is the omega of dark energy, not the omega.
Yes, omega of dark energy, yes.
So, but when you mix the cold dark matter and the hot dark matter models, aren't you kind of proposing that dark matter, you have two kinds of dark matter, or
no, it is the same kind, because what we know today is that I see what you're saying. So what we do know is that dark matter must be non-relativistic around structure formation. That's all we know. We don't know whether dark matter was a structure formation. That's much later, okay? So if dark matter experienced a production mechanism which is different from these standard ways, that's irrelevant for structure formation. It doesn't really matter. When we do introduce this mechanism of dark matter being produced from heavy decay, but it's still, even if including that, dark matter must be non-relativistic around structure formation. And we need to ensure that, and we did. So when the chi prime decay, chi is heavy, decay into dark matter, when you do the time evolution of dark matter at matter structure formation, dark matter is already non-relativistic. Was relativistic back then at the decay, but at the structure formation became non-relativistic. That's why M chi cannot be whatever you want, and M chi prime cannot be whatever you want. You are restricted by structure formation.
Okay.
Make sense?
Okay, let's thank again from Farinaldo.
All right, thank you.
And the last presentation is an empirical approach into cosmological constant by Ramon de Sá Pereira. Can you hear me, Ramon? Ramon? Ramon, we can hear you. We can't hear you, Ramon.
Ainda bem que ele é o último.
Tá mais 5 ou mais 10 minutos?
Eu acho que é bom, tipo, tirar as sessões de dele e voltar logo de só. Nós dois.
Quem que falou aqui?
Foi o Farinaldo. Parece que não.
Nelson Padilha não tá, ele vai voltar para a discussão. O Gabriel também não tá. Álvaro tá. Farinaldo, Ramon não tá. Ele pode fazer, quem quiser perguntar para o Álvaro. Se quiser perguntar para o Álvaro. Okay, so for those remote, I guess you understand what's going on. We dropped Ramon, which was going to speak now. And so we decided to enter the discussion session, and let's see what happens. Okay, some people on the discussion session will join back when it's the time of the discussion sections, which is in 20 minutes. But we have online Álvaro, which is the only one that of this evening session. That's the only one present. So Álvaro, if you are available, we can start the discussion session with you. And there is already a question for you.